Imagine a place where there is nothing, no light, no sound, no matter, not even the whisper of a single atom, an absolute void, a perfect emptiness. For centuries, this was our conception of space, a passive, silent stage upon which the drama of the cosmos unfolded. But what if this stage is not empty at all? What if the deepest, most profound silence is actually a roar of infinite potential? Modern physics has peeled back this veil of nothingness, and what it has revealed is one of the most unsettling and beautiful truths in all of science. The void is not empty. It is a seething, boiling ocean of energy, a phantom sea of constant creation and annihilation. This is the realm of zero-point energy, the hidden power of the universe, an invisible and inexhaustible reservoir that exists at every single point in space-time. It is the baseline hum of reality, the lowest possible energy state of the cosmos, a state which is, paradoxically, not zero. This is not a metaphysical speculation. It is a direct consequence of the laws of quantum mechanics. The uncertainty principle, first articulated by Werner Heisenberg, dictates that we can never know both the precise position and the precise momentum of a particle at the same time. This fundamental uncertainty extends to energy and time, in any field, in any system, even in a vacuum cooled to absolute zero. There must be a residual flicker of motion, an irreducible quantum jiggle. This is zero-point energy. It is the universe's insurance policy against absolute stillness, a law that decrees that nothing can ever truly be at rest. This constant vibration is not a chaotic or random noise. It is the fundamental symphony of the cosmos, a music that plays in the background of all existence. Every quantum field that makes up our reality, the electron field, the photon field, the Higgs field, is constantly vibrating, even in its ground state. These vibrations are not just a theoretical curiosity. They have real, measurable effects. They give rise to a constant stream of virtual particles, phantom entities that borrow energy from the vacuum to pop into existence for an immeasurably short time before annihilating each other and returning their borrowed energy to the void. We cannot see these particles directly, but we can see their shadows. The Casemir Effect, where two uncharged metal plates in a vacuum are pushed together by an invisible force, is a direct, experimental confirmation of their existence. The pressure of the virtual particles outside the plates is greater than the pressure between them, creating a net force. The void itself can push and pull. This discovery transforms our understanding of reality. Matter is not a solid, fundamental substance, but an excitation, a ripple, a concentrated vibration in these underlying quantum fields. The space we perceive as empty is not a passive backdrop, but the very source of everything we see, the invisible foundation upon which the fabric of time, space, and matter is woven. To understand zero-point energy is to understand that what we call nothing is actually the most potent something in the universe, a sea of infinite possibility from which all of reality may have been born. The idea that energy can exist in a perfect vacuum, in what we intuitively understand as nothingness, is one of the most profound paradigm shifts in the history of science. It directly challenges our classical though common-sense understanding of the world. For centuries, our physics was built on the idea that energy is a property of things, of particles, of waves, of systems. The notion that energy could be a property of emptiness itself was unthinkable. Yet, the evidence is undeniable. The Casemir Effect is not a subtle or theoretical correction. It is a measurable, physical force that can be detected in a laboratory. It is the macroscopic manifestation of the microscopic quantum foam, a direct testament to the fact that the void is alive with energy. But if this energy is real, where is it, and can we use it? This is where the mystery deepens. Zero-point energy is not like the energy stored in a battery or in a gallon of gasoline. It is a uniform, isotropic energy that pervades all of space. There is no gradient, no difference in potential that would allow us to easily extract it. To use energy, we need to create a flow from a high-energy state to a low-energy state, but zero-point energy is already the lowest possible energy state of the system. It is like trying to get water to flow out of the bottom of the ocean, and yet, the sheer amount of this energy is staggering. When physicists attempt to calculate the energy density of the quantum vacuum based on the principles of quantum field theory, they arrive at a number that is astronomically large. It is an energy density so immense that, if it were all gravitationally active in the way that normal matter and energy are, the universe would have collapsed into a black hole in the first fraction of a second of its existence. This enormous discrepancy between the theoretical calculation and the observed reality of our universe is known as the cosmological constant problem, or the vacuum catastrophe, and it is arguably the single greatest unsolved problem in all of fundamental physics. It tells us that there is something profound about the nature of vacuum energy that we do not yet understand. Perhaps there is a hidden symmetry of nature, a principle of supersymmetry, for example, where the contributions of different types of particles to the vacuum energy precisely cancel each other out, leaving only a tiny residual amount. Or perhaps our understanding of gravity itself is incomplete, and the vacuum energy does not gravitate in the same way as normal matter. Whatever the solution, the reality of this vacuum energy is not in doubt. Its most significant consequence may be playing out on the largest possible scales. The observed accelerating expansion of the universe, attributed to a mysterious dark energy, is one of the great puzzles of modern cosmology. The properties of this dark energy, a constant energy density that does not dilute as the universe expands, are remarkably similar to the properties of the vacuum energy predicted by quantum mechanics. Many cosmologists now believe that dark energy is, in fact, the macroscopic manifestation of zero-point energy, the faint, residual energy of the vacuum acting as a cosmic anti-gravity, pushing the universe apart. If this is true, then the fate of our cosmos, its ultimate journey into an ever-expanding, cold and dark future, is being dictated by the subtle, incessant quantum vibrations of empty space. The greatest mystery on the cosmological scale may have its roots in the deepest secrets of the quantum void. The allure of an infinite, ubiquitous energy source has inevitably captured the human imagination, giving rise to a subculture of invention, speculation, and science fiction centered on the idea of harnessing zero-point energy, the concept of free energy, of a device that can extract limitless power from the vacuum, has been a holy grail for inventors and theorists for decades. Patents have been filed, prototypes have been built, and countless claims have been made, often blurring the line between legitimate scientific inquiry and pseudoscience. The core idea behind many of these proposed devices is to create a localized asymmetry in the vacuum, a way to tap into the zero-point fluctuations and convert them into usable work. This is often imagined through resonant cavities or specially designed nanostructures that could, in theory, interact with the virtual particles of the vacuum, much like a windmill interacts with the wind. The Casemir Effect itself is often cited as a proof of principle. If the vacuum can exert a physical force, then in principle, that force can be used to do work. A hypothetical Casimir engine might involve two plates that are cyclically brought together and pulled apart, with the attractive Casimir force doing work in one part of the cycle. However, the scientific and engineering challenges are immense. The Casimir force is incredibly weak and only becomes significant at nanometer scale separations. Building a macroscopic engine that could overcome friction and other dissipative forces to extract a net positive amount of energy remains far beyond our current technological capabilities. Furthermore, there is a deep theoretical objection rooted in the laws of thermodynamics. The second law of thermodynamics, the law of entropy, states that you cannot build a perpetual motion machine of the second kind, a machine that extracts heat from a single thermal reservoir and converts it entirely into work. The quantum vacuum, in many ways, behaves like a thermal reservoir at absolute zero. Extracting energy from it would seem to violate this fundamental principle. Most mainstream physicists argue that while zero-point energy is real, it is the ground state of the universe, and you cannot extract energy from the ground state, just as you cannot get water to flow from the lowest point in a valley. Yet, the debate continues. Some researchers argue that the quantum vacuum is not a simple thermal system and that the classical laws of thermodynamics may not apply in the same way. They propose that through clever engineering, it might be possible to create a non-equilibrium state, a way to pump the vacuum to extract its energy. These ideas remain highly speculative and are on the very fringes of accepted physics. But they speak to a deep human desire, the desire for a clean, limitless, and universally available source of power. The story of zero-point energy is, in this sense, a modern myth. It is the story of a hidden cosmic power, a secret fire that, if it could be stolen from the gods of quantum mechanics, would transform human civilization forever. While the scientific consensus remains skeptical, the dream persists. And perhaps it is a necessary dream. The quest to understand and potentially harness zero-point energy, even if it ultimately proves impossible, is pushing the boundaries of our understanding of quantum mechanics, nanotechnology, and the very nature of energy itself. It is a quest that forces us to ask fundamental questions about the relationship between energy, information, and the structure of the vacuum. And in science, sometimes the questions are more important than the answers. While the dream of harnessing zero-point energy for power remains in the realm of speculation, its real, measurable effects are already shaping our world in tangible ways. The Casemir Effect, once a theoretical curiosity, has become a crucial consideration in the field of micro- and nano-electromechanical systems. At the scale of microns and nanometers, where the components of tiny machines are separated by incredibly small distances, the Casimir force is no longer negligible. In fact, it can become a dominant force, causing microscopic cantilever beams to stick to their substrates, a phenomenon known as stiction. For engineers designing these tiny devices, the Casimir force is a very real and often problematic aspect of the physical world that they must account for in their designs. They must develop special coatings and surface geometries to mitigate its effects. But what was once a problem is now being seen as a potential opportunity. Researchers are now exploring ways to engineer and control the Casimir force, to turn this invisible quantum pressure into a tool. By carefully designing the shape and material properties of surfaces, it is possible to modify the spectrum of zero-point fluctuations between them, and thus to tune the Casimir force. It is possible to make it repulsive instead of attractive, or to create a Casimir torque that can cause microscopic objects to rotate. This has opened the door to a new generation of nanotechnology based on quantum engineering of the vacuum. Imagine tiny, frictionless bearings that levitate on a cushion of repulsive Casimir force, or microscopic actuators driven by the modulated pressure of the quantum vacuum. These are not science fiction, they are active areas of experimental research. The Casemir Effect provides us with a direct, albeit subtle, handle on the energy of the void. It is our first, tentative step towards interacting with and manipulating the most fundamental energy field in the universe. This has profound philosophical implications. We are not just passive observers of the quantum world, we are learning to become active participants, to engineer the very fabric of emptiness. The effect is also a powerful pedagogical tool, a stark and beautiful demonstration that our intuitive, classical understanding of the world breaks down at small scales. It is a window into the quantum realm, a glimpse of a reality that is far stranger and more counterintuitive than our everyday experience would lead us to believe. The invisible force between two plates in a vacuum is a testament to the fact that the universe is governed by laws that are often hidden from our direct perception. Laws that can only be uncovered through the combined power of theoretical insight and precise experimentation. The Casimir Effect is more than just a clever experiment. It is a bridge between the abstract, mathematical world of quantum field theory and the concrete, physical world of force and motion. It is where the ghost-like dance of virtual particles becomes a real, measurable pressure, a pressure that is already being incorporated into the design of our most advanced technologies, and may one day be the driving force behind the machines of the future. The quantum vacuum is not just a stage for the fleeting dance of virtual particles. It is the very foundation upon which all of matter is built. Our classical picture of matter is one of solid, inert particles, like tiny billiard balls. But quantum field theory tells us that this picture is fundamentally wrong. A fundamental particle, like an electron, is not a solid object. It is a localized, vibrating excitation of a more fundamental entity, the electron field. This field, like all quantum fields, pervades all of spacetime. The particle we perceive as an electron is simply a place where this field is vibrating with a certain quantized amount of energy. When the field is not excited, when it is in its ground state, we perceive it as empty space. But even in this ground state, the field is still there, and it is still subject to the incessant zero-point fluctuations. This has profound consequences for the nature of matter. The electron is not an isolated entity. It is in constant, intimate interaction with the quantum vacuum. It is continuously emitting and reabsorbing virtual photons, the carriers of the electromagnetic force, dressing itself in a cloud of these phantom particles. This vacuum polarization effectively screens the electron's bare charge, meaning the electric charge we measure is not its true, intrinsic charge, but a value that has been modified by its interaction with the void. Similarly, the mass of a particle is not an intrinsic, fixed property. A significant portion of a particle's mass arises from its interaction with the various quantum fields that fill the vacuum. The Higgs field, for example, permeates all of space, and particles acquire mass by dragging against it. But even beyond the Higgs mechanism, the self-interaction of a particle with its own field, mediated by the virtual particles of the vacuum, contributes to its measured mass. In a very real sense, matter is bootstrapped into existence by its own interaction with the emptiness that surrounds it. This dynamic, energetic picture of matter helps to explain some of its most fundamental properties. The stability of atoms, for instance, is a quantum mechanical phenomenon that depends on the vacuum. In classical physics, an electron orbiting a nucleus should radiate away its energy and spiral into the center in a fraction of a second. The reason this does not happen is that the electron can only exist in specific quantized energy levels. These levels are determined by the electron's wave-like nature and its interaction with the electromagnetic vacuum. The lowest energy level, the ground state, is not at zero energy. It is a state of dynamic equilibrium with the zero-point fluctuations of the vacuum. The electron cannot fall any lower because there is no lower energy state available to it. The atom is stable because the void itself provides a floor, a baseline of energy below which it cannot go. This understanding has cosmological implications as well. The very first seeds of structure in the universe, the tiny density fluctuations that would later grow into galaxies and clusters of galaxies, are thought to have originated as quantum fluctuations in the vacuum during the period of cosmic inflation. The quantum foam of the early universe was stretched to astronomical scales by the rapid expansion, freezing these microscopic fluctuations into the macroscopic seeds of all the structure we see today. The universe is, in a very real sense, a macroscopic manifestation of the quantum vacuum. We live inside a frozen snapshot of the void's primordial turbulence. This completely inverts our traditional view of the relationship between matter and space. We no longer see space as a passive container for matter. Instead, we see matter as an emergent property of space, a temporary localized ripple on the surface of a deep and energetic quantum sea. The invisible foundation is the true reality. The solid world we perceive is just its fleeting expression. The relationship between zero-point energy and the laws of thermodynamics is one of the most challenging and debated topics in modern physics, highlighting a deep, unresolved tension between our understanding of the quantum world and the macroscopic world of heat and energy. The laws of thermodynamics are some of the most robust and universal principles in science. The first law, the conservation of energy, states that energy cannot be created or destroyed, only transformed. The second law, the law of entropy, states that the total disorder of a closed system always increases over time. The third law states that it is impossible to reach absolute zero temperature in a finite number of steps. Zero-point energy seems to sit uncomfortably with all of these. At first glance, the constant emergence of virtual particles from the vacuum seems to violate the first law. Where is this energy coming from? The answer, within the framework of quantum mechanics, lies in the energy-time uncertainty principle. Energy can be borrowed from the vacuum for a very short amount of time, as long as it is paid back quickly. The virtual particles are this borrowed energy, and their brief existence and subsequent annihilation ensure that, on average, energy is conserved, so the first law holds. But in a strange, probabilistic, quantum mechanical way. The real tension lies with the second and third laws. The third law states that as a system approaches absolute zero, its entropy approaches a minimum value, and all motion should cease. But zero-point energy dictates that quantum systems can never be completely at rest. Even at absolute zero, there is a residual energy and a residual quantum fluctuation. This does not necessarily contradict the third law, as the law is about the process of reaching absolute zero, but it does challenge our classical intuition about what absolute zero means. It is not a state of perfect stillness, but a state of minimum possible quantum motion. The deepest conflict is with the second law, the law of entropy. The second law is what gives time its arrow. It is why heat flows from hot to cold, why eggs break but do not unbreak, why our universe evolves from a state of order to a state of disorder. But zero-point energy seems to be a form of energy that is perfectly ordered and does not dissipate. It is a constant, coherent hum that does not seem to be subject to the relentless march of entropy. If we could extract this energy, we could theoretically build a machine that would run forever, seemingly violating the second law. Most physicists resolve this by arguing that zero-point energy is a non-thermal energy. It is not heat, and it cannot be used to do work in the same way as a hot gas. It is the ground state, and you cannot extract energy from the ground state. However, this raises a deeper question. If there is this vast reservoir of perfectly ordered entropic energy pervading the universe, why does the universe as a whole still seem to obey the second law? This tension may be a clue that our understanding of thermodynamics is incomplete. Classical thermodynamics was developed to describe systems of steam engines and gases. It may not be the final word on the thermodynamics of the quantum vacuum itself. Some theorists have proposed new frameworks, like quantum thermodynamics, that attempt to generalize the laws of heat and energy to the quantum realm. In these frameworks, concepts like entropy and temperature are redefined to account for quantum effects like entanglement and superposition. The resolution of the conflict between zero-point energy and thermodynamics is a work in progress, but it is a crucial one. It lies at the heart of our attempts to build a unified theory of physics, one that can describe both the microscopic world of quantum mechanics and the macroscopic world of our everyday experience. It is a puzzle that connects the deepest questions about the nature of energy, the arrow of time, and the ultimate fate of the universe. The puzzle of the universe's expansion is another area where zero-point energy takes center stage, acting as the prime suspect in one of cosmology's greatest mysteries. The discovery in the late 1990s that the expansion of the universe is not slowing down under the pull of gravity, but is in fact accelerating, was a profound shock to the scientific community. It implied the existence of a mysterious, repulsive force, a form of dark energy that is pushing the cosmos apart. The nature of this dark energy is completely unknown, but its properties are strangely familiar. It appears to be a form of energy that is inherent to space-time itself, with a constant energy density that does not dilute as the universe expands. This is exactly the behavior we would expect from the zero-point energy of the quantum vacuum. And so, the leading hypothesis is that dark energy and vacuum energy are one and the same. The silent, incessant hum of the quantum void is the engine driving the cosmic acceleration. This is a beautifully elegant and simple idea. It connects the largest scale phenomenon in the universe, its accelerating expansion, with the smallest scale phenomenon, the quantum fluctuations of the vacuum. It suggests that the fate of the cosmos is being written by the laws of subatomic physics. If this hypothesis is correct, then zero-point energy is not just a subtle and microscopic effect, it is the most dominant form of energy in the universe. Making up roughly 70% of the total cosmic energy budget, it is the invisible, the silent majority that is shaping the future of our reality. In this picture, the future is one of eternal expansion. As the universe grows larger, the density of matter and radiation will continue to decrease, while the density of vacuum energy remains constant. Eventually, vacuum energy will be the only significant component of the universe. Galaxies will recede from each other at ever-increasing speeds, eventually disappearing beyond our cosmic horizon. The universe will become an increasingly cold, dark, and lonely place, a scenario known as the Big Freeze. It is a future dictated by the relentless, repulsive pressure of the void. However, as we have seen, this elegant picture is marred by the cosmological constant problem, the colossal discrepancy between the theoretical calculation of the vacuum energy and the observed value. This discrepancy is so large that many physicists believe that the simple identification of dark energy with vacuum energy must be wrong. This has led to a host of alternative theories. Perhaps dark energy is not a constant, but is a dynamic entity, a new quantum field dubbed quintessence that is slowly rolling towards its minimum energy state. In this scenario, the rate of cosmic acceleration could change over time, leading to a different ultimate fate for the universe. Or perhaps the problem lies not with the energy of the vacuum, but with our understanding of gravity. Maybe general relativity needs to be modified on cosmological scales, giving rise to an apparent acceleration without the need for any new form of energy. These are all active areas of research, and the James Webb Space Telescope is providing crucial data to help distinguish between them by precisely measuring the expansion history of the universe at different epochs. Webb can help to determine if the properties of dark energy have changed over time. The nature of the universe's expansion is one of the most fundamental questions in all of science, and at its heart lies the enigmatic nature of the void, zero-point energy. Whether it is the silent engine of cosmic acceleration or a red herring in the search for dark energy, is a concept we must grapple with to understand our cosmic destiny. It is a puzzle that connects the beginning of the universe with its end, the quantum with the cosmos, and the deepest secrets of the void with the ultimate fate of all that we know. The quantum vacuum is not just a passive energy reservoir, it is a dynamic, creative medium, a quantum foam where the very fabric of spacetime is thought to be in a constant state of turmoil at the smallest possible scales. This concept, first envisioned by the physicist John Archibald Wheeler, takes the implications of the uncertainty principle to their logical extreme. If the energy of a field can fluctuate over short timescales, and if energy and mass are equivalent, then these energy fluctuations can, in principle, create tiny, fleeting curvatures in space-time. At the Planck scale, the incredibly small scale of 10 to the power of minus 35 meters, where the effects of quantum mechanics and gravity are thought to become equally important, space-time is no longer a smooth, a continuous manifold. Instead, it is a roiling, chaotic foam of tiny, transient wormholes and microscopic black holes, constantly bubbling into and out of existence. In this picture, the smooth spacetime of our macroscopic experience is just an average, a large-scale approximation of a much more violent and chaotic underlying reality. The quantum foam is a direct consequence of the zero-point energy of the gravitational field itself, just like the electromagnetic field. The gravitational field has a ground state energy, and its zero-point fluctuations are what create this foamy structure. This idea has profound implications for our understanding of reality. It suggests that the concepts of distance and duration, which seem so fundamental to us, may break down at the Planck scale. The very notions of here and there, before and after, may lose their meaning in this quantum fuzziness. Time itself may not be a continuous flow, but a series of discrete probabilistic jumps, a staccato rhythm played out on the foamy stage of the quantum vacuum. This is a radical departure from the smooth, continuous spacetime of Einstein's general relativity, and it is at the heart of the search for a theory of quantum gravity, a theory that can unify the two great pillars of modern physics. But the quantum foam is not just a theoretical playground for physicists. It may have real, cosmological consequences. Some theories propose that our entire universe may have originated as a single, large quantum fluctuation in a pre-existing quantum foam, a bubble that spontaneously nucleated and then rapidly expanded in the event we call the Big Bang. In this scenario, the universe is not a unique creation, but a natural, and perhaps common, outcome of the inherent restlessness of the void. This leads to the tantalizing idea of a multiverse, a vast ensemble of bubble universes, each with its own physical laws and constants, constantly budding off from an eternally inflating quantum foam. Our universe is just one bubble among many, a fortunate fluctuation where the conditions happen to be right for the emergence of stars, galaxies, and life. This is a speculative but powerful idea. as it provides a potential explanation for the apparent fine-tuning of our own universe's physical constants. We live in a universe that is hospitable to life because we could not live in one that wasn't. We are the survivors of a cosmic lottery. The concept of the quantum foam, born from the simple idea of zero-point energy, thus leads us to the grandest and most mind-bending of all cosmological ideas. It suggests that our entire reality, with all its vastness and complexity, may be nothing more than a temporary, fortunate ripple on the surface of an infinite, eternal, and endlessly creative quantum sea. The emptiness is not just the foundation of matter, it is the womb of worlds. The creative potential of the void, its ability to birth particles and perhaps even universes, is mirrored by its potential to act as a force of anti-gravity, a concept that has long been a staple of science fiction, but which finds a tentative, theoretical grounding in the physics of zero-point energy. Our classical understanding of gravity, as described by Newton and refined by Einstein, is that it is always an attractive force. Mass and energy curve space-time, and this curvature tells other mass and energy how to move, always pulling them together. But the accelerating expansion of the universe tells us that there must be a repulsive force at play on cosmological scales, a form of cosmic anti-gravity. As we have seen, the leading candidate for this is the zero-point energy of the vacuum. The key lies in the concept of negative pressure. In normal matter, pressure is a positive quantity that acts as a source of gravitational attraction alongside its mass energy. But a field with a constant energy density, like the quantum vacuum, has a strange and counterintuitive property. Its pressure is negative, and it is equal in magnitude to its energy density. When you plug this negative pressure into Einstein's equations of general relativity, it creates a gravitational repulsion. The void, in a sense, pushes itself apart. This is the theoretical basis for the anti-gravity effect of zero-point energy. While this effect is currently only observed on the vast scales of the cosmos, it has ignited speculation about the possibility of harnessing this phenomenon for technological purposes. If we could somehow engineer a region of space to have a much higher density of vacuum energy, or if we could manipulate the properties of the vacuum itself, could we create a localized anti-gravity field? This is the dream of warp drive and other exotic propulsion systems. A hypothetical warp drive, like the one proposed by the physicist Miguel Alcubierre, would not work by accelerating a spaceship through space, but by manipulating space-time itself. It would involve creating a bubble of space-time around the ship, contracting space in front of it and expanding space behind it. The ship itself would remain stationary within this bubble, while the bubble moves through space, potentially at superluminal speeds, without violating the local speed of light limit. The energy requirements for such a device, according to the original calculations, were astronomical, requiring more energy than exists in the entire visible universe. However, more recent theoretical work has suggested that by cleverly designing the shape of the warp bubble, the energy requirements could be drastically reduced, perhaps to the mass of a large planet. The problem is that these models still require the existence of exotic matter with negative energy density. And while the Casemir Effect does demonstrate a region of lower than normal vacuum energy, creating a macroscopic amount of stable, negative energy is far beyond our current capabilities and may be forbidden by the laws of physics. Despite these immense challenges, the anti-gravity potential of zero-point energy remains a tantalizing, if distant, possibility. It represents the ultimate technological ambition to graduate from being passengers on the currents of space-time to becoming its pilots. It is a dream that connects the deepest questions of quantum gravity with our most profound aspirations for a future among the stars. It is a reminder that the void is not just a source of cosmic expansion, but also a source of endless human imagination, a canvas upon which we project our hopes for a future where even the laws of gravity may one day be subject to our command. The symphony of the cosmos is played on an orchestra of quantum fields, and zero-point energy is its fundamental tuning note, the silent, ever-present hum against which all other melodies are played. This is not just a poetic metaphor, it is a deep physical truth. The properties of all the fundamental particles and forces in the universe are intimately tied to the properties of the quantum vacuum. The universe is not a collection of independent entities, but a holistic, interconnected system. and zero-point energy is the energetic medium that connects it all. Consider the very constants of nature, the charge of the electron, the strength of the fine structure constant, the mass of the Higgs boson. In our current theories, these are fundamental parameters that we must measure experimentally. We do not know why they have the values they do. But in a deeper, more complete theory, these constants may not be fundamental at all. They may be emergent properties of the vacuum, determined by the complex interplay of all the zero-point fluctuations of all the quantum fields. The values we measure may be the result of a cosmic settlement, an equilibrium state that the universe has fallen into. This is the idea behind theories like string theory, which posits that all the fundamental particles are just different vibrational modes of a single, underlying entity, a tiny, vibrating string. In this picture, the properties of the particles are determined by the way the string vibrates, which is in turn determined by the geometry of the extra, hidden dimensions of spacetime that string theory requires. The shape and size of these extra dimensions are properties of the vacuum, and thus the laws of physics themselves are a consequence of the vacuum structure. This leads to the stunning possibility that the laws of physics may not be universal in an absolute sense. If our universe is just one bubble in a multiverse, as the quantum foam concept suggests, then other bubble universes could have different vacuum states, different geometries for their extra dimensions, and therefore different physical laws. This provides a potential solution to the fine-tuning problem. The reason the constants of nature in our universe appear to be so finely tuned for the existence of life is because we live in one of the few universes where they are. In the vast cosmic symphony, there are countless dissonant, lifeless universes. We simply inhabit one of the rare, harmonious ones. This perspective transforms zero-point energy from a simple background noise into the very DNA of the cosmos, the source code that specifies the laws and constants of our reality. The silent notes of the vacuum are what determine the music of existence. The quest to understand zero-point energy is therefore not just a quest to understand a particular form of energy. It is a quest to understand the operating system of the universe. It is a search for the deepest logic of reality, the why behind the what. And as we listen more closely to the silent hum of the void, with instruments like the James Webb Space Telescope and the next generation of particle accelerators, we may begin to discern the structure of this cosmic score, to understand the principles that govern its harmony, and to perhaps, one day, learn to play a few notes of our own. The universe is a symphony, and we are the part of the symphony that has woken up and is beginning to listen to itself. It is the most profound and beautiful endeavor in all of human history. The profound interconnectedness of the quantum vacuum raises one of the most speculative, yet deeply compelling questions at the intersection of science and philosophy. Could there be a link between the zero-point energy field and the phenomenon of consciousness? This is a question that pushes the boundaries of scientific inquiry, venturing into territory that is often dismissed as mystical or pseudoscientific. And yet, the strange, non-local, and holistic nature of both the quantum vacuum and consciousness invites us to at least consider the possibility of a connection. Quantum mechanics has taught us that the universe is not a collection of separate, independent objects, but a web of interconnected probabilities. The observer effect, where the act of measuring a quantum system forces it to collapse from a state of multiple possibilities into a single, definite reality, has long suggested that consciousness may play a more active role in the universe than classical physics would allow. While most physicists interpret the observer effect as a result of the interaction of the quantum system with a macroscopic measuring device, and not necessarily with a conscious mind, a minority have long argued for a more direct role for consciousness. The theory of orchestrated objective reduction, proposed by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff, is one of the most well-developed of these models. It posits that consciousness arises from quantum computations occurring within microtubules, the protein skeletons of our brain's neurons. In this model, these quantum computations are not isolated. They are coupled to the zero-point fluctuations of the vacuum, the fundamental geometry of space-time. Consciousness, in this view, is a process of orchestrated collapse of the quantum wave function, a process that is not random, but is influenced by a form of Platonic information embedded in the Planck scale structure of the universe. The conscious mind, in a sense, is tapping into the fundamental information field of the cosmos, a field whose energetic manifestation is the zero-point energy. This is a highly speculative and controversial theory, and it lacks direct experimental evidence, but it is a scientifically testable one. It makes specific predictions about the quantum properties of the brain that could, in principle, be measured. But even beyond specific models like OR, the general idea of a connection between the vacuum field and consciousness resonates with many philosophical and spiritual traditions. The concept of a universal consciousness, a Brahman in Hinduism or a Tao in Taoism, a fundamental unified field of awareness from which all individual consciousness arises, has echoes in the modern physical concept of a unified quantum field that pervades all of space. Could the zero-point energy field be the physical correlate of this ancient philosophical idea? Could it be the interface between mind and matter, the medium through which intention and awareness can have a subtle but real influence on the physical world? This is a question that science is not yet equipped to answer, but it is a question that is becoming increasingly legitimate to ask. As our understanding of both the brain and the quantum vacuum deepens, we may find that the hard line we have drawn between the inner world of subjective experience and the outer world of objective reality is not as solid as we thought. Perhaps they are two sides of the same coin, two different manifestations of the same underlying information-rich and endlessly creative quantum reality. The possibility that the silent energy of the void is connected to the silent inner world of our own consciousness is a thought of breathtaking scope. It suggests that we are not just observers of the cosmic symphony, but are, in the most profound sense, an integral part of the music itself. Our thoughts, our feelings, our very awareness may be a resonance, a specific complex vibration of the same fundamental field that gives birth to stars and shapes the destiny of the universe. The technological implications of understanding and potentially manipulating the quantum vacuum are as vast as the cosmological ones. The development of quantum computers, for example, is a field that is both limited by and potentially empowered by zero-point energy. Quantum computers derive their immense processing power from their ability to harness the strange principles of the quantum world, like superposition and entanglement. A quantum bit, or qubit, can exist in a superposition of both 0 and 1 at the same time, allowing a quantum computer to explore a vast number of possibilities simultaneously. But this quantum fragility is also their Achilles' heel. Qubits are incredibly sensitive to their environment. Any stray interaction, any unwanted noise, can cause the delicate superposition to collapse, a process called decoherence, which destroys the quantum computation. And the most fundamental source of noise in the universe is the zero-point fluctuations of the quantum vacuum. The constant, random jiggle of the vacuum fields is a persistent background hiss that quantum engineers must constantly battle. They must develop sophisticated error correction codes and shielding techniques to protect their qubits from the inherent restlessness of the void. In this sense, zero-point energy is the ultimate adversary in the quest to build a large-scale, fault-tolerant quantum computer. But what if we could turn this adversary into an ally? Some theorists have proposed that it might be possible to engineer the vacuum itself, to create squeezed vacuum states where the quantum noise is reduced in one variable at the expense of increased noise in another. This could be used to create a quieter environment for qubits to operate in, pushing the limits of quantum computation. Even more speculatively, the quantum vacuum could one day become the ultimate communication medium. The phenomenon of quantum entanglement, where two particles can remain connected in such a way that a measurement on one instantly influences the other, regardless of the distance between them, seems to defy our classical notions of space and time. While it is not possible to use entanglement to send information faster than light, it does suggest a deep, non-local connectivity inherent in the fabric of reality. Some have speculated that it might be possible to modulate the vacuum state itself, to create vacuum telegraphs that could transmit information through the zero-point field. This would be a form of communication that does not involve the transmission of any particles or energy in the classical sense, but rather the propagation of a change in the state of the vacuum. Such a technology, if it were ever possible, would be truly revolutionary, offering a secure and potentially instantaneous form of communication across vast distances. The relationship between quantum information and the vacuum is a rich and complex one. It is a field where the deepest questions of fundamental physics meet the most practical challenges of next-generation technology. As we learn to build machines that can operate at the quantum level, we are also learning to interact with the universe in a new way, to speak its native language of probability, superposition, and entanglement. And in this dialogue with the quantum world, the silent, ever-present energy of the void is a constant partner, a source of both challenge and opportunity, the ultimate frontier for both our understanding and our technological ambition. The influence of the quantum vacuum is not confined to the exotic realms of quantum computing or cosmology. It leaves its subtle but detectable fingerprints on the very properties of the light and radiation that fill our universe. Light, in the classical picture, is an electromagnetic wave that propagates through a passive, empty space. But in the quantum picture, light is a stream of photons, and the space it travels through is a dynamic, fluctuating medium. The interaction between photons and the zero-point fluctuations of the vacuum leads to a number of fascinating and subtle effects. One of these is the phenomenon of vacuum birefringence, a prediction of quantum electrodynamics that has yet to be definitively observed. In the presence of a very strong magnetic field, the vacuum itself is predicted to behave like a birefringent crystal, meaning it would have a different refractive index for light of different polarizations. A beam of unpolarized light passing through such a magnetized vacuum would emerge slightly polarized. This effect is caused by the strong magnetic field influencing the behavior of the virtual electron-positron pairs that are constantly popping in and out of the vacuum. The field aligns their spins, effectively giving the vacuum a grain or an axis that affects the light passing through it, while the effect is incredibly small. Astronomers are searching for it in the light from magnetars, the neutron stars with the strongest magnetic fields in the universe. A confirmed detection of vacuum birefringence would be a stunning confirmation of one of the most counterintuitive predictions of QED, and a direct testament to the physical reality of the virtual particles of the vacuum. Another, more subtle, effect is the potential for the vacuum to influence the speed of light itself. According to Einstein's theory of relativity, the speed of light in a vacuum is a universal constant. However, some theories of quantum gravity suggest that at the Planck scale, the foamy, fluctuating nature of spacetime could affect the propagation of light. High-energy photons, with wavelengths approaching the Planck length, might interact more strongly with the spacetime foam, causing them to travel slightly slower than low-energy photons. This would be a tiny, energy-dependent violation of Lorentz invariance, the fundamental principle of relativity that underpins all of modern physics. Astronomers are searching for this effect by looking at the arrival times of high-energy photons from distant gamma-ray bursts. If high-energy photons from a burst consistently arrive slightly later than low-energy photons from the same burst, it could be a sign of this quantum gravity effect. So far, no such effect has been detected, which places tight constraints on many of these theories. But the search continues. These are incredibly challenging measurements, pushing the limits of our observational capabilities, but they are crucial. The light that travels to us across billions of light years from the distant universe is not just a picture of the past, it is a probe, a messenger that has traveled through the quantum vacuum for eons, carrying with it subtle imprints of its journey. By carefully deciphering these imprints, by looking for tiny changes in polarization, speed, or direction, we can use the light from the cosmos to study the properties of the void itself. It is a beautiful irony that by studying the brightest objects in the universe, we can learn about the nature of its deepest darkness, and by analyzing the properties of light, we can probe the very substance of emptiness. The vast, cold, and seemingly empty cosmic voids, the great deserts of the cosmos, are being transformed by our understanding of zero-point energy from places of nothingness into laboratories of fundamental physics. These are the most pristine regions of the universe, where the density of matter is so low that the effects of the quantum vacuum are not drowned out by the noise of stars, gas, and galaxies. It is here, in the deepest silence, that we can best hope to listen to the hum of the void. The existence of these voids is a natural consequence of the gravitational instability that drives the formation of the cosmic web. As gravity pulls matter together to form the great filaments and clusters, it necessarily leaves behind these vast, under-dense regions. But the properties of these voids, their size, their shape, their degree of emptiness are sensitive probes of the underlying cosmology. For instance, the nature of dark energy has a direct impact on the evolution of voids. A universe with a strong, repulsive dark energy will have voids that grow larger and emptier over time, as the cosmic acceleration pushes matter out of them more efficiently. By studying the statistics of voids at different cosmic epochs, astronomers can place constraints on the properties of dark energy, providing a powerful, independent check on the measurements from supernovae and the CMB. Webb is a powerful tool for this kind of void cosmology. Its sensitivity allows it to detect the faint, isolated dwarf galaxies that live within the voids, providing the crucial tracers needed to map their structure and evolution. But voids are not just tracers of dark energy, they may also be laboratories for testing our understanding of gravity. Some modified gravity theories, proposed as alternatives to dark energy, predict that the law of gravity should be different in low-density environments. In these theories, the gravitational force can be screened in high-density regions like our solar system, which is why we do not see any deviation from general relativity locally. But in the low-density environment of a cosmic void, this screening mechanism would be less effective, and deviations from Einstein's gravity might become apparent. By studying the motions of galaxies on the edges of voids and the weak gravitational lensing of background light by the sparse matter within them, we can test these modified gravity theories with unprecedented precision. The voids, in this sense, become the perfect place to look for a breakdown of our standard laws of physics. Finally, the voids are the best place to search for the subtle, large-scale signatures of the early universe. The faint temperature fluctuations in the cosmic microwave background are thought to be the seeds of all structure, but they have been processed and modified over billions of years of gravitational evolution. The voids, however, have evolved much less than the dense regions. They are, in a sense, a more direct, less processed window into the primordial universe. By studying the subtle patterns in the distribution of the few galaxies that do exist within voids, we may be able to detect the faint, non-Gaussian signatures predicted by some models of cosmic inflation, or even the aforementioned cosmic bruise that could signal a collision with another universe. The great cosmic voids are no longer the boring, empty spaces on the cosmic map. They are a new frontier, rich with information, a place where the secrets of dark energy, gravity, and the very beginning of the universe may be waiting to be discovered. They are a testament to the fact that in cosmology, as in so much of science, there is often as much to be learned from the absence of things as there is from their presence. The dynamic, energetic nature of the quantum vacuum, as described by zero-point energy, provides a new and powerful lens through which to view the very origin of the universe, offering a potential path to answering the ultimate cosmological question: why is there something rather than nothing? The traditional Big Bang model, while remarkably successful, has a fundamental limitation. It describes the evolution of the universe from a hot, dense state, but it cannot explain the origin of that state itself. The initial singularity is a point where the laws of physics break down, a moment of creation that lies outside the realm of scientific explanation. But the physics of the quantum vacuum allows for a different kind of beginning, a beginning that is not a violation of physical law, but a consequence of it. This is the concept of the universe from nothing, a concept that is often misunderstood. The nothing in this context is not the absolute, philosophical nothingness of non-existence. It is the quantum vacuum, a state devoid of matter and radiation, but rich with potential energy and subject to quantum fluctuations. In this picture, our universe could have been born from a spontaneous quantum tunneling event, just as a quantum particle can tunnel through an energy barrier that it classically could not overcome. The universe itself could have tunneled into existence from a state of nothing to a state of something. This idea was most famously developed by physicists like Alexander Vilenkin and Stephen Hawking in his no-boundary proposal. In this model, the universe did not have a beginning in time because time itself was created in the tunneling event. The question, what came before the Big Bang, becomes meaningless. Just as it is meaningless to ask what is north of the North Pole, the universe did not arise in time, it arose with time. It is a self-contained, self-creating system, born from the inherent quantum restlessness of the void. This is a profoundly beautiful and self-consistent picture. It removes the need for a supernatural creator or a first cause that lies outside of science. The universe, in this view, is the ultimate free lunch. The total energy of the universe is thought to be exactly zero. The positive energy of matter and radiation is perfectly balanced by the negative gravitational potential energy. Since the creation of a system with zero total energy does not violate the law of conservation of energy, the universe can, in principle, pop into existence from the vacuum without any external cause. The zero-point energy of the vacuum is the crucial ingredient that makes this possible. It is the energetic froth from which a zero-energy universe can spontaneously nucleate. This concept also leads naturally to the idea of a multiverse. If our universe can be created by a quantum fluctuation, there is no reason to think it was a unique event. The quantum vacuum is a fertile ground, and universes may be constantly bubbling into existence, each with its own set of physical laws and constants, determined by the specifics of the tunneling event. This provides an elegant, if unprovable, solution to the fine-tuning problem. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves on a planet that is hospitable to life. It is a selection effect. We could not have evolved to ask the question in any of the other, far more numerous, inhospitable universes. The origin of the universe is perhaps the deepest and most profound question that science can address. And while we may never have a definitive, final answer, the physics of zero-point energy has, for the first time, provided us with a plausible scientific framework for understanding how a universe like ours could come to be. It suggests that existence is not a strange and improbable exception, but perhaps the natural, and even inevitable, consequence of the laws of quantum mechanics playing out on the canvas of the void. Something exists because nothing, in the quantum sense, is fundamentally unstable. The creative, energetic, and foundational nature of the quantum vacuum, as described by the concept of zero-point energy, represents one of the most significant and revolutionary shifts in our understanding of reality since the birth of modern science. It is a concept that has taken us from a view of a static, passive, and empty space to a vision of a dynamic, creative, and endlessly energetic quantum sea. This is not just a change in a scientific model, it is a change in our fundamental relationship with the cosmos. We have learned that the solid world we perceive with our senses is a fleeting or emergent illusion, a temporary ripple on the surface of a much deeper but invisible reality. The particles that make up our bodies are not solid, immutable things, but localized vibrations of fields that extend throughout the entire universe. We are, in the most literal sense, woven from the fabric of the void. The forces that govern our world, from the light that allows us to see to the gravity that holds us to the earth, are mediated by the constant, fleeting dance of virtual particles born from the vacuum's energy. The very stability of the atoms that make us up is a delicate equilibrium with the zero-point fluctuations of the surrounding space. The grand architecture of the cosmos, the vast web of galaxies and voids, is a macroscopic fossil of the quantum turbulence of the early universe. The fate of our universe, its journey into an accelerating and perhaps eternal expansion, is being driven by the mysterious, repulsive pressure of the void itself, and the very origin of our reality. The event we call the Big Bang may have been a spontaneous quantum leap from the potential rich nothingness of the vacuum into the manifest existence we now inhabit. This is a worldview that is both profoundly humbling and deeply empowering. It is humbling because it reveals the severe limitations of our own perception and the vastness of our ignorance. 95% of the universe is made of dark matter and dark energy, mysterious entities whose nature we do not yet understand, but which are likely tied to the properties of the vacuum. Our entire existence is a fragile 5% exception in a vast, darkened, and invisible cosmos. But it is also empowering because it is a testament to the incredible power of the human mind. Through the abstract language of mathematics and the rigorous process of scientific inquiry, we have been able to deduce the existence of this hidden reality, to measure its effects, and to begin to understand its profound implications. We have built tools, like the James Webb Space Telescope, that allow us to peer into the void and listen to its secrets. The quest to understand zero-point energy is a journey to the very heart of reality. It is a quest that connects the smallest scales with the largest, the beginning of time with its end, and the most abstract theories of physics with the most tangible questions of our own existence. It is a journey that is far from over. The great puzzles, like the cosmological constant problem and the nature of dark energy, remain unsolved. But in grappling with these puzzles, we are pushing the boundaries of human knowledge and expanding our vision of what is possible. The silent, invisible energy of the void is the ultimate scientific frontier, a frontier that promises to yield new discoveries, new technologies, and a new, more profound understanding of our place in the cosmic symphony. The universe is stranger, more beautiful, and more deeply interconnected than we ever dreamed. And the key to its deepest secrets may lie where we least expected it, in the perfect, potent, and creative power of its own emptiness.
Imagine a force that cannot be seen, touched, or heard, yet its influence is woven into the very structure of the universe. It shapes galaxies, sculpts the birth of stars, protects planets, and guides the furious outbursts of black holes. This force doesn't emit light or sound. It doesn't announce itself with grand theatrics. Instead, it whispers in the silence of space, arranging matter and energy with quiet precision. It is the magnetic field, one of the most pervasive, mysterious, and transformative forces in the cosmos. In this first chapter of our journey through the magnetic universe, we explore what magnetic fields truly are, where they come from, and how they invisibly shape the grand architecture of everything we know. At its heart, a magnetic field is a region of space where magnetic forces act. These forces emerge whenever electric charges move, whether it's a current through a wire or particles spiraling at relativistic speeds through the vacuum of space. But this simple definition belies the profound significance of magnetic fields across scales, both atomic and cosmic. Every star, every planet, and even the vast voids between galaxies are imbued with magnetic fields, like unseen scaffolding. They thread through molecular clouds, sweep across spiral arms, wrap around black holes, and reach out into the intergalactic medium. They act as a silent blueprint, a hidden code embedded in the structure of the cosmos. And yet, despite their omnipresence, they remain invisible to our eyes. We detect their influence only indirectly through the light they polarize, the particles they accelerate, or the delicate dance of plasma they orchestrate. This is the paradox of magnetic fields. They are everywhere, and yet they must be inferred, reconstructed from the signatures they leave behind. Where magnetism begins. To understand where magnetic fields come from, we must begin at the smallest scale, the movement of charged particles. When an electron or proton moves, it generates a magnetic field. When countless particles move together like the molten iron churning in Earth's outer core, or plasma swirling in a young star, they create organized, large-scale magnetic fields that can persist for billions of years. This process is known as the dynamo effect. In rotating, electrically conductive fluids, the movement of particles generates electric currents, which in turn produce magnetic fields. These fields can feed back into the system, sustaining and amplifying themselves. It is a self-organizing phenomenon, where motion gives rise to force, and force reshapes motion. But the story doesn't start with planets or stars. Some scientists believe that magnetic fields may trace their origins all the way back to the beginning of time, to the inflationary epoch of the Big Bang. In those first fractions of a second, when space itself expanded faster than the speed of light, quantum fluctuations could have seeded tiny magnetic irregularities. Though feeble, these primordial magnetic fields may have been stretched and magnified across the universe, acting as the first magnetic imprints in a young cosmos. Magnetism as cosmic memory. One of the most elegant truths of the cosmos is that energy never disappears. It only changes form. Magnetic fields are a living memory of motion, fossilized into structure. They are records of rotation and turbulence, traces of collapse and expansion, echoes of cosmic violence and gentle order. In galaxies, these memories take form as structured magnetic fields aligned with spiral arms. As the galaxy rotates, its magnetic field is sheared and stretched, twisting into elegant helices that trace the curvature of stellar orbits. In star-forming regions, magnetic fields guide gas along filaments like invisible rails, concentrating matter where stars can be born. Even in the largest structures, we know galaxy clusters and the cosmic web magnetic fields are present. Intergalactic filaments stretch across millions of light years. And though their magnetic fields are faint, they are real. These fields shape the flow of matter across the universe and may help explain how cosmic rays, the high-energy messengers from deep space, traverse such vast distances. The magnetic shield of Earth. Closer to home, magnetic fields play a far more personal role. Earth's magnetic field, our planet's invisible guardian, shields us from the relentless assault of solar and cosmic radiation. Without it, the solar wind would strip away our atmosphere, leaving Earth as barren as Mars. Generated by the dynamo in Earth's liquid outer core, this geomagnetic field forms a bubble called the magnetosphere, deflecting charged particles and channeling some toward the poles. There, the collision of solar particles with our atmosphere creates the auroras, those luminous curtains of green, pink, and violet that dance above polar skies. They are the most visible expression of the magnetic field's protective role. Beautiful, ethereal, and vital. But the Earth's magnetic field is not static. It wobbles, reverses, and pulses over geological timescales. Magnetic poles flip, weaken, and migrate. These shifts are reminders that even the most seemingly stable structures in nature are dynamic, alive with internal motion. The magnetic lives of stars. Stars, too, are magnetic creatures. Within their fiery hearts, convective layers churn and rotate, generating magnetic fields that wax and wane in cycles. Our own sun experiences a roughly 11-year magnetic cycle, during which sunspots, solar flares, and coronal mass ejections rise and fall in intensity. These magnetic storms hurl vast quantities of plasma into space, sometimes striking Earth and disrupting satellites, power grids, and communications. Solar magnetism is not merely an academic curiosity. It is a force that tangibly touches our technological civilization. Massive stars, nearing the end of their lives, may intensify their magnetic fields to extreme degrees. In their death throes, they can collapse into neutron stars or black holes, objects where magnetic fields take on staggering proportions. The remnants of stellar magnetism in these objects can shape the behavior of matter and radiation in ways we are only beginning to understand. A magnetic thread through time. From the early whisperings of quantum fluctuations to the modern cry of radio pulses from distant galaxies, magnetic fields thread through the entire story of the cosmos. They are not merely side effects or curiosities, they are participants, sculptors, and archivists of cosmic history. Every region of space bears the fingerprint of magnetism. Some fingerprints are bold and etched like those of pulsars or magnetars. Others are subtle, woven into the background like the faint fields in cosmic voids. But all of them are part of a deeper story, one in which the motion of matter, the twisting of fields, and the rise of structure are intimately linked. To understand magnetic fields is to understand how the universe organizes itself, how chaos becomes order, how collapse becomes creation, how silence becomes music. Galactic magnetism, the architecture behind the arms. In the grand architecture of the universe, magnetism is a silent thread, a force that neither dazzles like starlight nor deafens like explosions, but one that shapes, protects, and organizes on scales both intimate and infinite. It moves unseen, yet leaves a signature in everything, from the graceful sweep of a galaxy's arms to the auroras that dance over polar skies. If gravity is the sculptor of form, then magnetism is the composer of motion and rhythm. It guides, it channels, it shields, and in this part of our journey, we trace its influence through the luminous spirals of galaxies and into the very cores of planets, where swirling metals whisper their secrets in magnetic tongues. This is a story of cosmic weavings of how galaxies breathe with magnetism and how planets, like Earth, live beneath its invisible wings. Look up at the night sky and behold the Milky Way, a glowing swath of light arcing from horizon to horizon. This seemingly tranquil vista hides the intricate dance of charged particles and invisible forces. In galaxies, magnetic fields are not mere passengers, they are partners in motion. They trace the spiral arms, entwining themselves with gas, dust, and light. Though far weaker than Earth's field, typically just a few microgauss, these galactic magnetic fields stretch across tens of thousands of light years, subtly orchestrating the rhythm of cosmic life. But how does such a delicate force arise on such enormous scales? At the heart of every galaxy lies chaos, clouds of ionized gas swirling, stars being born and dying, supernova shockwaves sweeping across interstellar space. Amidst this turmoil, a dynamo effect unfolds. Charged particles in motion generate currents, and those currents, in turn, produce magnetic fields. This feedback loop, amplified by turbulence and rotation, is what transforms faint, primordial seed fields into the vast magnetic tapestries we observe today. In spiral galaxies like our own, the magnetic field lines often align with the arms, as if following the galaxy's rotational flow. This alignment isn't random. It's evidence of how motion sculpts magnetism. As the interstellar medium rotates, it stretches and twists the field lines, shaping them into coherent, large-scale structures. These magnetic patterns help stabilize gas clouds, prevent them from collapsing too quickly, and even regulate where and when stars can form. The very shape of a galaxy is inseparable from the forces that bind it, and magnetism is one of them. High-energy particles, known as cosmic rays, zip through the universe at nearly the speed of light. They are born in violent places, exploding stars, black holes, supernova remnants. But despite their energy, their journey is rarely straight. Galactic magnetic fields catch them like a net, forcing them to spiral, scatter, and reroute across the interstellar medium. This behavior does more than delay their arrival to our detectors. It changes the story of how energy is transported through galaxies. Magnetic fields confine cosmic rays, trapping them within galactic disks, where they interact with matter and light, influencing heating, ionization, and chemical evolution. They become more than particles. They become messengers carrying energy, triggering reactions, and lighting up the sky through synchrotron radiation. Synchrotron radiation, emitted when cosmic rays spiral along magnetic field lines, gives us a way to see the invisible in radio wavelengths. These signals reveal the structure and strength of galactic magnetic fields, offering astronomers a window into their elusive patterns. How do we study something we cannot see? Light holds the key. When light passes through a magnetized medium like a cloud of interstellar plasma, it gets twisted. This effect, known as Faraday rotation, changes the polarization angle of light depending on the strength and orientation of the magnetic field along the line of sight. By studying these twists, astronomers can map the otherwise hidden architecture of magnetism. Another method lies in observing polarized starlight. Dust grains in interstellar space tend to align themselves with local magnetic fields, causing the light that passes through them to become polarized. Measuring this polarization allows scientists to deduce the direction of the magnetic field projected on the sky. Together with Faraday rotation, these techniques build a three-dimensional view of cosmic magnetism. With modern radio telescopes like the Very Large Array and the upcoming Square Kilometer Array, we are poised to unravel these invisible threads in unprecedented detail. Each data point, each polarized signal, adds a brushstroke to the vast canvas of the cosmic magnetic web. Closer to home, magnetic fields take on a more personal meaning. Earth's magnetic field is not just a scientific curiosity, it is a shield, a sculptor of habitability, and the quiet protector of every breath we take. Generated deep within the outer core, where molten iron and nickel churn in slow, convective motion, our planet's magnetic field emerges through the dynamo effect. The movement of conductive material creates electric currents, and those currents, looping through the planet's interior, produce a magnetic field that extends thousands of kilometers into space. This magnetosphere deflects the solar wind, a stream of charged particles from the sun that could otherwise strip our atmosphere and sterilize the surface. Without this shield, Earth might resemble Mars, dry, cold, and barren. Instead, we have a sky that dances. The auroras, those curtains of green and violet light that ripple above the poles, are born from this interaction, when solar particles are funneled by the magnetic field toward Earth's upper atmosphere. They collide with oxygen and nitrogen, igniting light. It is a cosmic ballet. The sun's fire meets Earth's magnetic grace. Each planet tells a different story of magnetism. Jupiter, the giant, hosts the most powerful magnetic field of any planet in our solar system, generated by a core of metallic hydrogen under immense pressure. Its magnetosphere extends millions of kilometers, enveloping moons like Io in radiation belts and sparking intense auroras far beyond Earth's scale. Mars, by contrast, is a planet that lost its voice. Once, it may have had a global magnetic field, but it vanished billions of years ago. Today, only remnant crustal fields remain, a patchwork of magnetism embedded in its rocks. Without a strong magnetic shield, the solar wind has gradually eroded Mars's atmosphere, leaving behind the thin veil of gas we see today. Venus, so similar to Earth in size and composition, offers another paradox. Despite its similarities, Venus has no global magnetic field. Its slow rotation and perhaps the absence of a convecting metallic core prevent the dynamo from forming. The result, Venus faces the sun's fury largely unprotected, and its thick atmosphere, while still present, bears the scars of ion loss and solar stripping. These planetary contrasts underscore a vital truth. Magnetic fields are not mere adornments, they are determinants. They shape a planet's atmosphere, surface conditions, and ultimately, its ability to support life. What makes a planet habitable? Liquid water, a stable climate, the right chemical ingredients, all are essential. But above them all stands an invisible requirement, a magnetic field. Without it, a planet's atmosphere may not survive. The solar wind, relentless and charged, strips away molecules unless something pushes back. Earth's magnetic field plays this role. It has held our atmosphere close for billions of years, allowing oceans to form, life to flourish, and oxygen to accumulate. Mars lost that battle. Its magnetic silence speaks volumes. The water it once held, now frozen or escaped, was a casualty of its vulnerability. Its potential for life, once real, was curtailed not by distance from the sun or the absence of carbon, but by the quiet loss of its shield. And so, in our search for life beyond Earth, magnetic fields may become a crucial filter. A distant exoplanet may orbit in the habitable zone, may have oceans, even continents, but if it lacks a magnetic field, it may also lack the time and protection necessary for life to take hold. Galaxies and planets are not islands. They are knots in the grand tapestry of the cosmos, connected by magnetism, threads of influence and structure, from the arms of spiral galaxies to the iron hearts of terrestrial worlds. Magnetic fields weave through time and space, whispering the rules by which stars are born, planets are shielded, and life, fleeting and fragile, may find a place to begin. We have only begun to understand these threads. With each new telescope, each signal twisted by Faraday's hand or lit by synchrotron glow, we draw closer to the truth that in a universe of light and gravity, magnetism is the quiet force that holds the music together. Magnetic fields in starbirth and cosmic jets. In the silent shadows of nebulae and the glowing hearts of newborn stars, magnetism whispers its influence. It is an unseen hand guiding the genesis of stars, threading through the dense clouds of gas and dust, sculpting the very architecture of cosmic nurseries. Here, in these quiet, luminous cradles of creation, magnetic fields play a role so vital, so intricate, that without them, the stars we gaze upon each night might never have come to be. And yet, their work doesn't stop at birth. Across vast gulfs of space, in the blazing throats of black holes and neutron stars, magnetism becomes a force of dramatic spectacle, launching cosmic jets that stretch across galaxies, shaping the dynamics of galaxies themselves. Let us begin in the heart of the molecular cloud, a region of interstellar space rich in hydrogen, cool and dark, yet primed with potential. These clouds are the raw material for stars, the cocoons where gravity battles against pressure and magnetic tension to ignite nuclear fire. For decades, astrophysicists have studied these regions, puzzled by a profound question: how does such a massive cloud collapse into a dense, luminous star without spinning itself apart in the process? The answer, in large part, lies in magnetic braking. As a molecular cloud collapses, it inherits angular momentum from its rotation, which, if left unchecked, would cause it to flatten and fragment chaotically. But magnetic fields act as regulators, like cosmic brakes. They channel angular momentum away through Alfvén waves, ripples of magnetic energy carried through plasma, allowing the cloud to contract in a controlled, stable fashion. Without this magnetic dissipation, star formation would be inefficient, unstable, and chaotic. It is the magnetic field that ensures a quiet orchestration, a slow, measured descent toward fusion and light. But magnetic fields are not passive observers. They also act as dynamic participants. Within collapsing clouds, magnetic field lines thread through filaments of gas, aligning with the flow of material, directing it inward toward gravitational centers. Observational studies using polarized light from dust grains. Tiny, irregular particles that align themselves with magnetic fields have confirmed this alignment. These observations, enabled by instruments like the Planck satellite and the James Webb Space Telescope, reveal a sky not just full of stars, but interwoven with invisible lines of magnetic structure. This magnetic alignment does more than guide gas. It helps regulate fragmentation, determining how many stars will form and how closely they will cluster in high-mass star-forming regions. Magnetic fields can resist the turbulent forces that would otherwise tear clouds apart, enabling the formation of massive stars that seed their environments with heavy elements and energize their surroundings with ultraviolet radiation. Yet even as they birth stars, magnetic fields can store and suddenly unleash immense energy, one of the most fascinating processes in astrophysics. Magnetic reconnection occurs when twisted and sheared magnetic field lines snap and reform, releasing tremendous energy in the process. This phenomenon, well known in solar flares on our Sun, also occurs in star-forming regions and young stellar objects, injecting localized heat into the cloud and altering ionization states that affect the chemistry and collapse dynamics. Reconnection is not just a violent outburst, it's a sculptor's chisel, subtly shaping the pace and pattern of star formation. By heating local pockets of gas, it can create temperature gradients that influence where and when stars emerge. In highly magnetized environments, these reconnection events may even generate outflows jets of material expelled at high speed from young protostars that carve cavities in their natal clouds and regulate further accretion of material. These protostellar jets, small cousins of the colossal relativistic jets seen from black holes, represent another triumph of magnetism, though far less energetic than their supermassive counterparts. They obey similar physics as material accretes onto a young star from a surrounding disk. Magnetic field lines are wound into a helical shape by the star's rotation. This twisted configuration channels a fraction of the infalling material outward in a narrow, collimated stream. Observations of Herbig-Haro objects, shock fronts where jets slam into surrounding gas, testify to the violent precision of this process. In these jets, the interplay between magnetism and plasma dynamics becomes vivid. The jets are magnetically dominated, meaning that the magnetic pressure exceeds the thermal or kinetic pressures of the material. This dominance provides stability, allowing the jets to travel vast distances, sometimes light years, without dispersing. Like needles of fire stitched through the interstellar fabric, they pierce the darkness with order and energy. And as with stars, so too with the monsters of the cosmos, around neutron stars and black holes, where gravity becomes extreme and space-time bends toward infinity. Magnetic fields once again take the lead, accretion disks dense. Hot rings of matter spiraling inward generate powerful magnetic fields as ionized particles move at high speed. These fields don't just guide the infall of matter, they can extract rotational energy from the central object itself. In the case of black holes, this occurs via the Blandford's-Nijek mechanism. Here, twisted magnetic field lines tap into the rotational energy of a spinning black hole, launching jets of plasma outward along the poles. These jets are among the most luminous and powerful structures in the universe, visible across billions of light years. Their synchrotron radiation light, emitted by charged particles spiraling in magnetic fields, reveals the structure and dynamics of the field itself, like ink revealing the shape of invisible currents. Neutron stars, particularly pulsars and magnetars, also drive jets. In these environments, magnetic fields reach titanic strengths, bending atomic structures and warping space itself. The fields around magnetars are so intense they can trigger starquakes, fractures in the crust of the neutron star caused by magnetic stress, which in turn release bursts of gamma rays. These outbursts are among the brightest events observed in the universe. Cosmic jets, whether from infant stars or ancient black holes, are not merely byproducts, they are sculptors in their own right. The energy they inject into the surrounding environment can heat interstellar gas, inhibit or trigger star formation, and enrich the medium with metals. In galaxy clusters, supermassive black hole jets help regulate cooling flows, preventing runaway starbursts that would otherwise destabilize galactic cores. In this grand ballet, magnetic fields provide choreography. They maintain order in chaos, channel the fury of collapsing clouds, and tether the raw energy of spinning singularities. They are the weavers of jets, the governors of angular momentum, the invisible guides of stellar destiny. Yet, for all their power, they remain elusive, measurable only through their influence on light and matter. We trace them through polarization, infer their presence from synchrotron radiation, and map their twists through Faraday rotation. They speak to us not in words, but in orientation, acceleration, and spin. Our understanding of magnetic fields in starbirth and cosmic jets is still growing. Every observation, every simulation, every moment when a telescope captures a jet slicing through the void or a protostar firing a burst of plasma tells a deeper story of how magnetism shapes the universe. Magnetism in exotic objects, white dwarfs, neutron stars, and magnetars. In the vast tapestry of the cosmos, certain celestial objects stand out not just for their brilliance, but for the enigmatic magnetic forces they harbor. White dwarfs, neutron stars, and magnetars, stellar remnants of once mighty stars, are laboratories of extreme physics, where magnetism reaches unfathomable intensities. These compact objects, though diminutive in size, wield magnetic fields that challenge our understanding of matter, energy, and the very fabric of space-time. White dwarfs are the dense cores left behind after low to intermediate mass stars exhaust their nuclear fuel, typically about the size of Earth, but with masses comparable to the Sun. These stellar remnants are composed mostly of electron-degenerate matter, while many white dwarfs are relatively quiescent. A subset exhibits magnetic fields ranging from a few kilogauss to over a gigagauss, up to 1 billion times stronger than Earth's magnetic field. The origin of these intense magnetic fields in white dwarfs has been a subject of debate. One prevailing theory suggests a fossil origin, where the magnetic field is a remnant from the progenitor star, amplified during the star's collapse. Another hypothesis involves binary interactions, where the merger of two white dwarfs or accretion from a companion star could generate a dynamo effect, amplifying magnetic fields to observed levels. Recent studies have also proposed that internal processes during the cooling of the white dwarf itself might play a role in magnetic field generation. A particularly intriguing discovery is that of white dwarf pulsars. These are white dwarfs that exhibit pulsar-like behavior, emitting periodic bursts of radiation due to their rapid rotation and strong magnetic fields. The identification of such objects blurs the line between traditional white dwarfs and neutron stars, suggesting a continuum of magnetic phenomena across different stellar remnants. When massive stars undergo supernova explosions, their cores can collapse into neutron stars, objects so dense that a single teaspoon of their material would weigh billions of tons. These neutron stars often possess magnetic fields trillions of times stronger than Earth's. making them some of the most magnetic objects in the universe. Pulsars, a type of neutron star, emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space, and if aligned correctly with Earth, they can be detected as regular pulses, hence the name pulsar. The mechanism behind this emission involves the acceleration of charged particles along magnetic field lines, producing radiation across the electromagnetic spectrum. The geometry of a pulsar's magnetic field is complex. The magnetic axis is typically inclined relative to the rotation axis, leading to a lighthouse effect as the star spins. Models of pulsar magnetospheres consider various regions where particle acceleration occurs, such as the polar cap, slot gap, and outer gap. These regions are crucial for understanding the emission mechanisms and the observed pulse profiles of pulsar. Among neutron stars, magnetars stand out for their colossal magnetic fields, which can exceed 10^15 Gauss. These fields are so intense that they can distort atomic structures and influence the properties of the vacuum itself. Magnetars are relatively rare, with only a few dozen confirmed in our galaxy, but their extreme magnetic environments make them subjects of intense study. Magnetars exhibit a range of high-energy phenomena, including sporadic X-ray bursts, giant flares, and persistent X-ray emission. These events are thought to be powered by the decay and reconfiguration of the magnetar's magnetic field. For instance, sudden shifts in the magnetic field can fracture the star's crust, releasing vast amounts of energy in the form of X-rays and gamma rays. One of the most intriguing aspects of magnetars is their potential connection to fast radio bursts. Fast radio bursts are millisecond-long bursts of radio waves originating from distant galaxies. While their exact origin has been a mystery, recent observations have linked some FRBs to magnetar activity. In 2020, a bright radio burst was detected from the galactic magnetar SGR 1935+2154, providing compelling evidence for this connection. The mechanisms behind fast radio bursts emission from magnetars are still under investigation. One model suggests that crustal fractures in the magnetar generate Alfvén waves, magnetohydrodynamic disturbances that propagate through the magnetosphere, leading to coherent radio emission. Another theory involves magnetic reconnection events, where twisted magnetic field lines snap and reconnect, releasing energy that powers the radio bursts. To probe the extreme environments of magnetars and other compact objects, astronomers rely on space-based observatories like NASA's Chandra X-ray Observatory and the Nuclear Spectroscopic Telescope Array. These telescopes provide high-resolution X-ray observations, crucial for studying the high-energy emissions from these objects. Chandra's observations have revealed detailed structures in magnetar magnetospheres, including hotspots on the star surface and extended emission regions. Nuclear Spectroscopic Telescope Array, with its sensitivity to higher energy X-rays, complements Chandra by detecting hard X-ray components of magnetar spectra. Together, these observatories have been instrumental in characterizing the spectral and temporal properties of magnetar outbursts. For instance, observations of the magnetar 1E 1841-045 in the Kes 73 supernova remnant have provided insights into its emission mechanisms. The combined data from Chandra, Nuclear Spectroscopic Telescope Array, and other telescopes have helped model the magnetar's spectrum as a combination of thermal and non-thermal components, shedding light on the physical processes at play. Studying the magnetic behavior of white dwarfs, neutron stars, and magnetars offers more than just astrophysical insights. It provides a natural laboratory for testing the laws of physics under extreme conditions. The intense magnetic fields and densities present in these objects allow scientists to explore phenomena like quantum electrodynamics in regimes unattainable on Earth. For example, The vacuum birefringence effect, a prediction of quantum electrodynamics where a strong magnetic field can polarize the vacuum, might be observable in the light emitted from magnetars. Detecting such effects would be a significant milestone in confirming aspects of quantum theory. Moreover, understanding the magnetic field evolution in these compact objects can inform models of stellar evolution, supernova mechanisms, and the behavior of matter at nuclear densities. As observational techniques advance, and as more sensitive instruments come online, our comprehension of these magnetic titans will continue to deepen, unraveling the mysteries they hold. Cosmic webs and the future of magnetism. Across the vastness of space, far beyond the glowing spiral arms of galaxies and the flickering birthplaces of stars, stretches a hidden force that binds the cosmos in ways we are only beginning to grasp. Magnetism is not confined to planets or stars. It stretches into the fabric of the universe itself, threading its way through galaxy clusters and weaving across the intergalactic medium. In this final act of our exploration, we turn to the magnetic threads that lace the cosmic web, the most elusive and expansive structures shaped by this invisible architect. Galaxy clusters are colossal structures, gravitationally bound gatherings of hundreds or even thousands of galaxies. Within these clusters lies not just visible matter, but also immense amounts of hot, ionized gas known as the intracluster medium. This gas, glowing in X-rays, fills the space between galaxies, and permeating through it is a magnetic field that, while much weaker than those found on stars or planets, plays an outsized role in shaping the dynamics of the cluster. These intracluster magnetic fields typically measure a few microgauss in strength comparable to the average galactic magnetic field, but they extend across millions of light years, making them vast in scope and influence. The origins of these cluster-scale magnetic fields are not fully understood. Some theories suggest that they are relics of the early universe, primordial fields amplified by gravitational collapse and turbulence. Others propose that galaxies inject magnetized plasma into the intracluster medium through winds and jets, seeding the space between galaxies with magnetic energy. Over time, these seed fields are amplified by motions in the plasma itself, via a cluster-scale dynamo effect or through mergers and shock waves that stir and strengthen the magnetic lines. Detection of these subtle, extended magnetic fields requires sensitive and clever observational techniques. One of the most powerful tools is Faraday rotation, the twisting of the polarization angle of light as it passes through a magnetized medium. By observing polarized radio waves from distant quasars as they shine through the intracluster medium, astronomers can infer the strength and orientation of the intervening magnetic field. Another vital method is synchrotron radiation, which occurs when high-energy electrons spiral along magnetic field lines. This emission, detected primarily in radio wavelengths, serves as a beacon of magnetic activity in regions that would otherwise appear dark and empty. To probe these faint and far-reaching signals, astronomers have turned to a new generation of telescopes. The low-frequency array has already begun mapping magnetic fields in the cosmic web by detecting weak synchrotron signals between galaxy clusters. The Very Large Array, with its high-resolution radio imaging, continues to refine our understanding of magnetic interactions on smaller scales. The Atacama Large Millimeter/Submillimeter Array contributes by revealing the fine structures of magnetized dust and gas in galaxy formation zones. Yet the most ambitious of these tools is the upcoming Square Kilometer Array, which promises to revolutionize our understanding of cosmic magnetism. Square Kilometer Array, once operational, will be the most sensitive radio telescope ever constructed, with thousands of antennas spread across continents. it will survey the sky with unprecedented depth and resolution. One of its goals is to map the magnetic field of the universe on the largest scales, tracing the magnetic filaments of the cosmic web, understanding the evolution of magnetism over cosmic time, and detecting the faint whispers of primordial magnetic fields that may have formed shortly after the Big Bang. Square Kilometer Array will allow us to conduct deep polarization surveys, measure Faraday rotation across millions of background sources, and study synchrotron emission from even the most diffuse intergalactic structures. Magnetic fields are not passive players in the cosmos, in the intergalactic medium. They guide the movement of plasma, influence the propagation of cosmic rays, and help regulate the thermal properties of gas during the formation of galaxies. These fields can shape the inflow of matter, determine where stars are born, and suppress or trigger star formation depending on their configuration. In galaxy clusters, magnetic fields help stabilize the intracluster medium against gravitational collapse, influence the morphology of radio relics and halos, and affect the mixing and transport of heat and metals across vast distances. Moreover, magnetic fields may be key players in the cosmic feedback loop, the cycle through which energy is transferred from black holes and massive stars back into the galactic and intergalactic environment, jets from active galactic nuclei, shaped and powered by magnetic forces, inject both energy and magnetic flux into the surrounding medium. This feedback helps regulate galaxy growth, limits the cooling of gas in clusters, and seeds the intergalactic medium with both heavy elements and magnetic fields. Thus, the magnetic field acts as a channel for energy redistribution on a cosmic scale. Philosophically, the study of cosmic magnetism invites us to reconsider the nature of the universe itself. Magnetism, invisible to the eye yet ever present, serves as a metaphor for the hidden structures that govern the cosmos. Its subtlety masks its strength, and its ubiquity is easily overlooked, yet it holds galaxies together, protects planets, sculpts stellar nurseries, and may even connect us to the earliest moments of creation. The more we peer into its patterns, the more we recognize its role as one of the silent shapers of existence. There is also a melancholic beauty to this story. Magnetic fields are transient on cosmic timescales. They evolve, decay, and vanish as stars die. Galaxies merge, and the universe expands, yet they leave behind traces, echoes in the radiation, patterns in polarization, subtle bends in the paths of particles that testify to their presence long after they are gone. In this way, they remind us of the impermanence of even the most powerful forces, and of the importance of listening closely to the universe's quietest whispers. As we enter an era of precision cosmology, magnetic fields will no longer be sidelined as secondary phenomena. They are emerging as central players in our understanding of the universe, linking the microphysics of particles to the macro scales of structure formation, from the heart of magnetars to the filaments of the cosmic web. Magnetism pervades every level of reality. And as we map its influence, we gain not only knowledge of the forces at work, but also a deeper sense of our place in this grand and mysterious universe. As we come to the end of this journey through the unseen architecture of the cosmos, we're left with a new appreciation for something so invisible, so silent, and yet so powerful. Magnetic fields are not just lines on a diagram or abstract forces in physics equations. They are the breath between stars, the sculptors of galaxies, the protectors of worlds, the whisperers of origin stories written not in words, but in charged particles and cosmic light. We've traced them from the molten hearts of planets to the glowing arms of spiral galaxies, from the crackling surface of magnetars to the tangled threads of the intergalactic medium. We've seen how they guide cosmic rays, shape jets that erupt from black holes, regulate the birth of stars, and protect fragile atmospheres on distant worlds. They carry memory and momentum. They weave through time. And yet, for all we now know, magnetic fields still leave us with questions as vast as the space they move through. What gave birth to the universe's first magnetic field? Was it seeded in the furnace of the Big Bang, or did it arise from deeper laws still waiting to be discovered? Why do these fields persist in patterns so intricate and coordinated across billions of light years? Is magnetism merely a consequence of charged motion, or is it a fundamental rhythm of the cosmos? A beat we have only just begun to hear. There is something profoundly humbling in the realization that all around us and within us, magnetism flows. Our own Earth is wrapped in its shield. The sun's storms reach out to us through it. Even the magnetic atoms in our blood once danced to the field lines of ancient stars. It reminds us that we are not separate from the cosmos. We are threaded into it. Our instruments: square kilometer array, low frequency array, Atacama, large millimeter array. The Event Horizon Telescope are tuning into the whispers of these fields with growing clarity. Soon, we may map them not just in patches, but across the full tapestry of the cosmic web. We may use them as tools, as timekeepers, even as probes into physics beyond the standard model. They may one day tell us about the symmetry of the vacuum, about hidden particles, about the very fabric of space-time. But more than that, magnetic fields connect us to the poetry of the universe. They are the invisible ink that shapes galaxies, the geometry that guides the dance of matter, the memory of movement long past, and perhaps, just perhaps, the signature of something deeper still. In a world that is so often loud, it's fitting that the universe holds its structure together with something quiet. So the next time you look up at the night sky, remember this: what you see is only part of the story. Behind the light, behind the stars, lies an intricate lattice of magnetism stretching across the void, binding the galaxies, pulsing faintly in the dark. This is the music of the cosmos. This is the voice of the invisible. And it is still being written. Thank you for joining this exploration of the cosmic magnetic field. If this journey sparked wonder, leave a comment, subscribe, and share it with someone curious. The universe is waiting. What is the most powerful thing in the universe? Is it the incandescent, almost unimaginable fury of a supernova, a stellar cataclysm so vast, so energetic, that for a fleeting, glorious, yet terrifying moment in cosmic time, it can outshine an entire galaxy, a swirling city of many billions of individual stars? The universe whispers its secrets in many voices, some barely audible, others roaring across cosmic oceans of space-time. Imagine, if you will, a journey not through terrestrial landscapes, but through the very fabric of existence, where the familiar laws of nature are stretched to their absolute limits, and sometimes, perhaps, even beyond. This is an odyssey into the heart of cosmic power, a meditation on forces that sculpt galaxies, birth stars, and orchestrate the grand, indifferent, and often profoundly beautiful symphony of creation and destruction. Is it, perhaps, the silent, inexorable, and utterly inescapable might of a black hole, a true gravitational behemoth that bends the very fabric of space and time into unimaginable, almost paradoxical knots, a cosmic vortex from which not even light itself, the fastest thing in existence, can ever hope to escape? These are not mere academic questions. They are invitations to contemplate the raw, untamed energies that have shaped everything we see and everything we are. Or could it be something even more ethereal, more focused, more insidiously destructive, like a searing, concentrated beam of high-energy radiation? A cosmic death ray, perhaps. That could, in less than the blink of a human eye, erase an entire planet from existence, sterilizing its surface, boiling its oceans, and extinguishing any nascent, fragile spark of life that might have dared to emerge their power in this vast, dynamic, and often surprisingly violent universe. Clearly manifests itself in a truly bewildering, almost infinite, and often quite awe-inspiring variety of different physical forms. Some of these immense cosmic forces are overtly, terrifyingly, and almost indiscriminately destructive, capable of tearing apart entire stars from within, shredding vast, ancient galaxies through colossal collisions, and perhaps even, in their most extreme theoretical manifestations, reshaping the very architecture, the fundamental geometry of space-time itself. Other, perhaps more subtle, yet equally fundamental forces work far more quietly, much more patiently, almost invisibly on cosmic scales, yet they are no less powerful in their ultimate effect. These are the forces that gently, yet persistently, hold the intricate, delicate structures of the cosmos together against the relentless, disorganizing pull of universal entropy. The forces that bind fundamental particles into atoms, atoms into complex molecules, molecules into stars and planets, stars into vast, majestic galaxies, and galaxies, in turn, into immense, interconnected, web-like cosmic superstructures that span billions of light years. And then, beyond these more familiar manifestations of power, there are perhaps a select, enigmatic few cosmic phenomena, certain forces or events, so utterly strange, so profoundly extreme in their physical manifestation, so far beyond our current, limited terrestrial experience and our present theoretical grasp of fundamental physics, that we still, despite all our remarkable scientific progress and our ever-sharpening observational tools, do not yet fully or even adequately understand precisely how they truly work, what their ultimate, deepest origins might be, or what their far-reaching implications might eventually prove to be for the future evolution of the universe. And perhaps, ultimately, for our own distant, uncertain destiny as a species within it. This is a voyage into the melancholy beauty of cosmic apocalypse, not as an end, but as a constant, transformative process. Let us then embark on an intellectual exploration, a conceptual journey to the very edges of currently known physics, and perhaps just a little way beyond those established frontiers, into the intriguing, often unsettling, realm of the truly, unimaginably powerful, the cosmic forces and the cataclysmic events that relentlessly, and often quite spectacularly, push the very known limits of what physical reality itself can seemingly handle, what it can possibly endure without fundamentally breaking down. We will venture, in our minds and through the lens of science, into diverse physical realms where ambient energy densities, fundamental gravitational fields, and other extreme physical conditions reach almost unimaginable, often theoretically challenging, and sometimes even seemingly paradoxical extremes. These are realms where the familiar, everyday laws of nature, as we currently understand them from our relatively placid, terrestrial environment, are often stretched to their absolute breaking point, and sometimes, perhaps, even beyond, into entirely new, currently unknown domains of physical law. And it is precisely in these extreme, crucible-like environments that the universe, in its full, awesome, and often terrifying majesty, most clearly reveals its almost limitless capacity for both breathtaking, intricate creation and for ultimate, all-encompassing, and perhaps even beautifully melancholic, apocalyptic destruction. This is, then, a voyage into the very heart of true cosmic power, a profound and perhaps somewhat humbling quest to try and understand the colossal, often invisible, yet undeniably formative titans that relentlessly, and often quite indifferently, shape our universe, our galaxy, our solar system, and ultimately, even our own fragile, precious existence within it. Prepare to witness a universe forged in power, where every ending heralds a new, often violent, beginning. Our grand exploration into the diverse realms of cosmic power begins not, perhaps, with the immediately colossal or the overwhelmingly vast, but rather with the infinitesimally small, with nature's own, incredibly efficient, and almost unbelievably powerful subatomic particle accelerators. On very rare, entirely unpredictable, and spatially random occasions, a single, solitary, fundamental particle, an entity far, far smaller in physical size than any single atom, can silently, invisibly, and with almost unimaginable kinetic energy, strike the tenuous upper layers of the Earth's protective atmosphere. And it can do so with more raw, concentrated kinetic force than a hard, dense baseball that has been pitched at blistering, record-breaking speed by a highly trained, world-class professional athlete. These extraordinary, almost ethereal messengers from the depths of space are the ultra-high-energy cosmic rays, often referred to by astrophysicists by the acronym UHCRs. And these individual solitary particles rank, without any shadow of a doubt, among the most extraordinarily powerful, most energetically concentrated, and certainly most enigmatic subatomic particles ever to have been observed and meticulously studied by modern science. They do not, it is important to note, arrive at Earth in great visible or easily detectable swarms or in ethereal, faintly glowing clouds, as more common, lower energy astrophysical phenomena like ordinary stardust, diffuse interstellar gas, or the gentle, continuous solar winds that constantly bathe our entire solar system typically do. Instead, these unique, ultra-high-energy cosmic rays almost always arrive, one by one, sporadically, almost stealthily, and with no discernible advance warning, like infinitesimally small, silent, invisible, yet incredibly potent, microscopic bullets that have been fired with unimaginable force from the deepest, darkest, and most mysterious reaches of distant, intergalactic space. Each one of these individual UHCRs is, in essence, a lone, intrepid, and incredibly resilient cosmic traveler, having successfully, and against immense odds, traversed truly immense, almost unimaginably vast cosmic distances, distances that often span many millions, or in some cases, even many billions, of light years, to finally, purely by chance, reach us here on our relatively small, insignificant planet Earth. And when they do eventually, randomly arrive, when they finally, catastrophically collide with an unsuspecting, ordinary atom of nitrogen or oxygen residing high up in our planet's tenuous upper atmosphere, they sometimes, in that single, almost instantaneous, and incredibly violent interaction, release a concentrated burst of pure energy that is significantly greater by many orders of magnitude than any human-made machine, any terrestrial particle accelerator, no matter how large or sophisticated, has ever, even for the most fleeting, infinitesimal fraction of a second, been able to artificially produce or effectively control here on Earth. The sheer audacity of such a tiny entity carrying such immense power speaks to the universe's capacity for surprise, a subtle violence woven into the quiet of space. To truly, and perhaps somewhat viscerally, put this astonishing, almost unbelievable, natural cosmic power into some kind of relatable, human-scale perspective. Consider for just a moment the most advanced, most powerful, and certainly most expensive single-particle accelerator currently existing and operating anywhere on our planet Earth, the magnificent Large Hadron Collider, or LHC. A truly monumental ring of thousands of powerful superconducting magnets and incredibly sophisticated. Ultra-sensitive particle detectors, a machine that stretches for a full 27 kilometers in its main circular circumference, and which is buried deep beneath the picturesque Franco-Swiss border countryside near the city of Geneva. This absolutely incredible, awe-inspiring machine, a true triumph of modern, cutting-edge engineering, advanced technology, and sustained international scientific collaboration involving thousands of scientists and engineers from all around the world, is designed to accelerate and then smash together beams of ordinary protons, the positively charged, relatively stable hearts of hydrogen atoms, at speeds approaching an astonishing 99% of the absolute, unbreakable speed of light in a vacuum. In doing so, the LHC routinely produces, in these incredibly energetic head-on proton-proton collisions, staggering particle interaction energies of up to 13, or sometimes, with recent upgrades, even slightly more, trillion electron volts per individual collision event. That is, by any normal human standard or everyday experience, an absolutely enormous, almost unimaginable amount of highly concentrated kinetic energy for a single, fundamental subatomic particle to possess. It is certainly enough focused energy, in fact, to allow experimental particle physicists to directly, and with increasing precision, probe the very deepest, most fundamental building blocks of ordinary matter to effectively recreate, for incredibly fleeting, almost infinitesimal instants of time, the extreme ultra-high energy physical conditions that are thought to have existed in the universe's very first fiery moments just after the Big Bang. And it allows them to actively, and with great hope, search for entirely new, currently undiscovered fundamental particles and perhaps even new, unknown fundamental forces of nature that might lie beyond our current, remarkably successful, yet known to be incomplete, standard model of particle physics. But even these truly prodigious, almost unbelievable, human-generated particle energies, as impressive and as scientifically valuable as they undoubtedly are still utterly, almost laughably, and completely dwarfed in their sheer magnitude by those routinely carried by some of these naturally occurring, and still largely mysterious, ultra-high energy cosmic rays that arrive from the depths of space. Some of these individual, solitary celestial interlopers have now been reliably and repeatedly detected by specialized cosmic ray observatories around the world as possessing total kinetic energies of over 100 quintillion electron volts, a truly mind-boggling, almost astronomical amount of energy to be carried by a single subatomic particle. That's literally many millions of times more concentrated kinetic energy per single individual particle than anything humanity, with all its accumulated scientific knowledge and technological prowess, has ever, even remotely, managed to artificially build, control, or experimentally achieve here on our planet Earth. Imagine, if you can even begin to, all that almost inconceivable, focused power, all that incredible kinetic energy, packed tightly, almost impossibly, into something that is physically far smaller in its actual physical size than even a single solitary proton. It's a concentration of raw, physical energy that is almost too much for the ordinary human mind to readily believe or to fully, intuitively comprehend in all its profound physical implications for the nature of the universe. These cosmic whispers carry the echoes of cataclysms, supernova, or the churning hearts of active galactic nuclei. Events so remote their light might have begun its journey before our solar system even formed. Most ordinary, everyday cosmic rays, the ones that constantly, and for the most part, relatively harmlessly, and largely unnoticed, bombard the Earth's upper atmosphere every single second of every single day, are actually believed to be born or accelerated in relatively common, though still impressively energetic, astrophysical events that occur throughout our galaxy. These include, for example, powerful eruptive solar flares that sporadically burst forth from the magnetically active surface of our own sun, or they can be generated in the rapidly expanding, turbulent shock waves of ordinary exploding stars. The Type II supernova that frequently occur within the confines of our own Milky Way galaxy as massive stars reach the end of their lives. And these more common, almost garden variety, cosmic rays are by direct comparison to their much rarer, much more energetic ultra-high energy cousins, typically quite relatively low in their individual particle kinetic energy, usually ranging from a few million to perhaps a few billion electron volts. Energies that are easily achievable and often surpassed by our modern terrestrial particle accelerators. But these truly ultra-high energy versions, these UHECRs, these champions of the Cosmic Particle Energy League, are qualitatively, fundamentally, and almost certainly in their origin, very, very different indeed. They don't, for instance, seem to originate from anywhere nearby in our local cosmic neighborhood. Their arrival directions on the sky, though difficult to pinpoint precisely, do not correlate well with any known, obvious, or particularly energetic astrophysical sources located within our own Milky Way galaxy, nor even, it seems, from any of our closest neighboring galactic companions within the local group of galaxies. They're almost unimaginable. Immense individual particle energies strongly, almost unequivocally, imply that they must have been somehow accelerated to these incredible, near-light speed, relativistic velocities somewhere very, very far away from us, perhaps originating from sources located many millions, or even billions, of light-years distant, far, far beyond the gravitational confines of our local galactic group, in some of the most extreme, most violent, most powerful, and most energetic physical environments that the entire observable universe has to offer. Supermassive black holes, accreting matter at furious rates, or the hyper-violent aftermath of gamma-ray bursts remain prime suspects in this cosmic mystery, their distant rage echoing in these solitary, energetic particles. We've only, to date, and despite many decades of dedicated observational effort by specialized cosmic ray observatories around the world, managed to definitively, unambiguously observe and measure a relative, precious handful, perhaps only a few dozen or so in total, of these truly, exceptionally ultra-high energy cosmic rays. Those possessing individual particle energies clearly exceeding, say, 50 or 60 quintillion electron volts. And unfortunately, to further compound the already immense observational challenge, their incoming incident paths as they traverse the vast, almost empty expanses of intergalactic and then interstellar space, on their long journey towards Earth, are known to be significantly, and often quite randomly, bent, twisted, deflected, and scattered by the relatively weak, but incredibly pervasive and extensive magnetic fields that are now known to thread throughout all galaxies, and also, albeit even more tenuously, throughout the vast, largely empty spaces that lie between the galaxies themselves. So, accurately, precisely tracing these observed UHECRs back from their arrival direction at Earth to their specific, distant, and often very faint points of origin in the deep cosmos. In order to definitively pinpoint their specific cosmic accelerators is currently a nearly impossible, and certainly a profoundly, exceptionally challenging observational and astrophysical task for contemporary astronomers and particle astrophysicists. The universe guards its most powerful secrets well, dressing them in veils of distance and magnetic deflection. Furthermore, it's important to realize that these primary incident UHECR particles don't actually themselves ever manage to strike the solid ground of the Earth directly, which is, perhaps, quite fortunate for us and for life on Earth in general, given their immense individual energies. Instead, when these highly energetic primary cosmic rays first encounter the Earth's relatively dense atmosphere, they typically, and almost immediately, violently collide with the atomic nuclei of ordinary atmospheric atoms, usually nitrogen or oxygen atoms, residing high up, many tens of kilometers above the planet's surface. This initial, incredibly energetic collision completely, catastrophically smashes those unfortunate atmospheric atoms apart, thereby creating, in its immediate aftermath, a vast, subsequent, and rapidly developing cascade, a veritable, ever-widening shower of myriad other newly created, secondary, and generally somewhat lower energy elementary particles such as pions, kaons, muons, electrons, positrons, photons, and even some neutrinos. One single, tiny, almost infinitesimal, yet incredibly energetic, primary UHECR particle, upon its initial impact with the upper atmosphere, effectively and almost instantaneously sets off an absolutely enormous, spatially extensive atmospheric particle shower. An event technically known to physicists as an extensive air shower that can, by the time it eventually reaches the Earth's surface, have spread out laterally over many square kilometers in area. Specialized, ground-based cosmic ray detectors, often consisting of many individual, widely separated detector stations, are then used to simultaneously pick up, record, and precisely time the arrival of these numerous, spatially distributed secondary air shower particles. Scientists then meticulously try to piece together, through careful, complex computer-based reconstruction algorithms that analyze the precise arrival times, the measured energies, and the spatial distribution of all these detected secondary particles. Precisely what kind of energetic interaction must have happened high up in the atmosphere many microseconds earlier. And from that reconstructed information, they then try to infer, with as much accuracy as possible, what the crucial physical properties, particularly the initial energy, the approximate arrival direction, and perhaps even the particle type of the original unseen primary cosmic ray particle must have been before it initiated that vast atmospheric cascade. This indirect detection is a testament to human ingenuity, turning the atmosphere itself into a vast detector. In very remote, often quite desolate, and geographically extensive places around the world, such as, for example, the vast open pampas grasslands of western Argentina, which is home to the currently largest such facility in the world, the Pierre Auger Observatory. Dedicated teams of international scientists and engineers have painstakingly built and now operate truly huge, sprawling arrays of these specialized cosmic ray particle detectors. These arrays often consist of many hundreds or even thousands of individual, independent detector stations, which are typically spread out systematically, often in a regular grid pattern over incredibly wide geographical areas, sometimes covering many thousands of square kilometers of terrain, all patiently, continuously watching the skies above, day and night, for the fleeting, telltale observational signs of these incredibly rare, yet scientifically invaluable. Ultra-high-energy atmospheric cascade events. When a primary UHECR successfully hits the Earth's upper atmosphere, it then sends this characteristic, relativistically moving, almost pancake-shaped wave or front of myriad secondary particles cascading downwards towards the ground at very nearly the absolute speed of light. These extensive, ground-based detector arrays then effectively, and with remarkable precision, listen for the precise moment of arrival of that subtle yet detectable particle wave at each of their individual detector stations. And then, by meticulously measuring the precise arrival times and the deposited energies of all the detected secondary particles at these many different, widely separated detector locations across the array, they can then accurately and often with surprising detail reconstruct the overall physical size, the precise three-dimensional shape, and the total energy content of that entire extensive air shower as it swept over the observatory. It's a remarkably indirect, yet surprisingly effective and scientifically robust method of detecting and characterizing these otherwise invisible primary cosmic ray particles. It is, in some ways, conceptually somewhat like trying to accurately figure out precisely what kind of massive, unseen rock made a very big splash in a dark, distant, and otherwise completely inaccessible pond by only being able to carefully look at and meticulously analyze the detailed physical properties of the expanding, concentric system of outgoing water ripples that eventually, and often much later, manage to reach the distant shore where your detectors are located. From the precise shape, the measured amplitude, the arrival timing, and the evolving energy distribution of those observed secondary water ripples, these dedicated scientists patiently, painstakingly, and with great ingenuity, try to accurately learn as much as possible about the original size, the precise incident direction, and most importantly, the incredible, almost unimaginable initial kinetic energy of that original, unseen and long since disappeared stone. The silence of these remote observatories belies the violent messages they strain to hear from the cosmos. Even though we, as a global scientific community, have now successfully built these truly enormous, incredibly sophisticated, and often quite expensive dedicated ground-based observatories specifically to try and systematically study them, these truly ultra-high-energy cosmic rays, the most energetic particles known in the universe, still remain exceptionally, almost frustratingly, rare celestial events from our observational perspective here on Earth. On average, current best estimates from these observatories suggest that only about one single such UHECR, possessing an individual particle energy clearly exceeding, say, 50 or 60 quintillion electron volts, actually physically hits each single square kilometer of the Earth's entire upper atmosphere roughly only about once every century or so. That incredibly low arrival rate means, quite starkly, that you could patiently, diligently, and with unwavering dedication watch the entire sky above you, day and night, for your entire human lifetime, and you would still, in all statistical likelihood, never, ever directly, personally witness the arrival or the atmospheric signature of one of these truly extraordinary, universe-traversing, and still largely enigmatic elementary particles. If we could, however, somehow, someday, fully and comprehensively understand their precise astrophysical origins, their currently unknown acceleration mechanisms, and their detailed propagation characteristics as they journey through the vast, magnetized expanses of intergalactic and interstellar space, then we might, just might, be able to gain invaluable, perhaps even revolutionary, new physical insights into some of the most extreme, most energetic, most violent, and currently most mysterious physical environments that are known to exist anywhere in the entire observable universe. We might even, perhaps, if we are particularly fortunate and insightful, stumble upon entirely new, currently unknown, and perhaps even paradigm-shifting laws of fundamental physics, new physical principles, new particles, or new interactions that only truly manifest themselves, or become clearly apparent at these almost unimaginably high, ultra-relativistic energy scales that are currently far, far beyond anything we can even remotely hope to achieve or to directly probe. In our most powerful cutting-edge terrestrial laboratory experiments and particle accelerators, perhaps these lone voyagers carry clues to the very texture of spacetime or the echoes of creation itself. The universe, it seems, still holds the championship title for high-energy particle physics, a humbling reminder of our nascent understanding. Now, let us turn our scientific attention and our perhaps somewhat apprehensive human imagination from these tiny, individual, almost invisible, yet incredibly, almost unbelievably energetic cosmic ray bullets. Particles which, as we've noted, typically travel largely alone and almost entirely unseen through the vastness of the cosmos until they happen to strike our atmosphere. Let us shift our focus instead to something far more tangible from our everyday experience, far more immediately visceral in its potential impact, and certainly, potentially far more directly, globally, and apocalyptically destructive on a planetary, and perhaps even a biospheric scale, namely, the cataclysmic, truly earth-shattering, and often species-ending hammer-blow dynamics of what are known as mega-asteroid impacts. Unlike those subtle, individual, and largely indirect cosmic rays, a typical mega-asteroid, one capable of causing global devastation, is a veritable, solid, tangible mountain, often many kilometers across in physical size, composed primarily of dense, primordial solar system metal and heavy stone, hurtling silently, menacingly, and often with very little advance warning, through the cold, dark, and largely empty blackness of interplanetary space, on a potential collision course with a planet like our own Earth. The sheer, almost unimaginable amount of raw kinetic energy that would be instantly, catastrophically released upon its violent impact with a relatively fragile, life-bearing planet like Earth is truly, almost incomprehensibly enormous, far, far beyond, by many orders of magnitude, anything that human beings, with all our accumulated technological prowess and our unfortunate history of destructive invention, have ever, even in our most extreme, globally threatening moments, managed to artificially create or deliberately unleash upon ourselves or our planet. This is not a whisper, but a deafening roar, a cosmic hammer blow that can rewrite planetary history in an instant. A relatively modest, by some cosmic impact standards at least, 10-kilometer diameter asteroid, an object roughly the size of Mount Everest, but composed of much denser rock and metal, and traveling at typical interplanetary encounter speeds of perhaps 20 to 30 kilometers per second, if it were to directly, catastrophically strike the Earth, would instantaneously, in a fraction of a second, release more raw, concentrated, destructive energy than all the thousands of powerful nuclear weapons currently existing in the combined arsenals of all the nuclear-armed nations on the entire planet, if they were all somehow gathered together and detonated simultaneously at a single point on the Earth's surface. And that's not just a one-time energy release equivalent, mind you. Such an impact would likely release that much energy, or even significantly more, not just once, but potentially many, many times over, depending on the asteroid's precise initial mass, its exact chemical composition, its incoming trajectory, and its final impact velocity relative to the Earth. The underlying fundamental physics of such a catastrophic cosmic impact event, in principle at least, relatively simple, straightforward, and well understood by planetary scientists and physicists, based on fundamental principles of mechanics, thermodynamics, and shockwave propagation. Yet its predicted and historically observed physical consequences for a planet like Earth, and for any life that might exist upon it, are utterly, almost indescribably terrifying and potentially, truly apocalyptic in their scope and severity. A truly massive, solid object. The asteroid, moving at an incredibly high interplanetary speed, often many tens of times faster than a speeding rifle bullet, carries with it an absolutely immense, almost unimaginable amount of stored kinetic energy. And all that colossal, planet-shattering kinetic energy must, by the fundamental, inexorable, and unbreakable physical law of conservation of energy, go somewhere, be rapidly, violently transformed into other, equally destructive forms of energy, primarily heat, light, sound, and mechanical shock, when that massive, speeding rock suddenly, catastrophically, and almost instantaneously stops its immense forward orbital motion upon impact. It stops very, very suddenly, indeed, in a tiny fraction of a second, effectively smashing violently, almost explosively, into the Earth's relatively thin, fragile solid outer crust, much like a colossal, cosmic-sized sledgehammer, swung with unimaginable force. In the immediate, fiery and chaotic aftermath of such a truly titanic mega-impact event, the Earth's solid crust, and even parts of its upper mantle, at the precise point of impact, would instantaneously, almost unbelievably, melt, completely liquefy, and even partially vaporize into an incandescent, superheated plasma, all due to the immense pressures and temperatures generated by the sudden, extreme compression of material. This molten and vaporized rock would then be violently, explosively ejected outwards in all directions from the impact site, some of it thrown high up into the atmosphere, some even potentially escaping Earth's gravity altogether and being blasted out into interplanetary space. The ground itself, for hundreds, perhaps even thousands, of kilometers around the impact site, would tremble uncontrollably, violently, almost like the skin of a struck colossal cosmic gong. Immense, powerful seismic shock waves, far, far more energetic and destructive than those generated by even the largest, most powerful naturally occurring earthquakes ever recorded in human history, would rapidly, relentlessly tear their way through the planet's deep rock layers, propagating outwards from the impact point like ripples on a pond, but with far more devastating consequences. These seismic waves would catastrophically crack, shatter, and liquefy the solid surface of the Earth for hundreds, perhaps even many thousands of kilometers in all directions from the primary impact point. Within mere seconds, or at most, just a few short minutes, of the initial impact, a truly massive, almost unimaginably large impact crater, a vast, gaping, circular wound gouged deeply into the planet's surface, would be violently, explosively excavated by the sheer force of the impact and the subsequent rebound of compressed rock. Such a crater would often be significantly deeper, by many kilometers, than any human-made excavation ever attempted, and it could potentially measure many hundreds of kilometers in its overall diameter, a truly planetary-scale scar. The melancholy beauty of such destruction lies in its raw, indifferent power, a force that resets planetary clocks. The intense, almost unimaginable heat that would be generated by the initial impact itself, primarily from the extreme, sudden compression of both the impactor and the target rock, and also from the friction of re-entering ejecta, would be more than enough, almost instantaneously, to ignite widespread, raging, and almost uncontrollable fires for many thousands of kilometers in every conceivable direction outwards from the primary impact site. Entire vast continental forests, sprawling grasslands that might stretch from horizon to horizon, perhaps even entire. Unfortunate ecosystems located anywhere within this vast, global inferno would spontaneously, almost explosively, burst into flame, completely incinerating everything remotely combustible that lay within their path. Any animals, any unfortunate, exposed life forms that were unlucky enough to be caught out in the open, anywhere within this vast, rapidly expanding radius of fiery incandescent destruction, simply tragically wouldn't stand a chance of survival. They would be almost instantly vaporized by the intense heat, or quickly burned alive by the ensuing global firestorm. Winds far exceeding any normal meteorologically generated hurricane speeds that we are familiar with on Earth today. Winds perhaps reaching many hundreds or even thousands of kilometers per hour would be instantly generated, driven not by conventional atmospheric pressure gradients or differential solar heating of the Earth's surface, but rather by the sheer, raw, explosive, outward propagating force of the impact blast itself. These super hurricane force winds would relentlessly, mercilessly scour the entire landscape, bare for vast distances around the impact site, uprooting trees, leveling buildings, and carrying vast quantities of dust, debris, and burning embers far across continents and even oceans. And, at the same time, almost unimaginable, truly colossal quantities of fine dust, black soot from the widespread global wildfires, shattered rock debris from the impact crater excavation, and various other vaporized terrestrial and impactor materials would be violently, explosively thrown high up into the Earth's upper atmosphere, with some of the finest, highest velocity ejecta particles even potentially reaching up into the stratosphere, or perhaps in the most energetic impacts, even being blasted completely out into space, only to then slowly, gradually, and ominously fall back down again towards the Earth's surface under the influence of gravity, often many days, weeks, or even months after the initial primary impact event had already long since passed. The sky itself would become an enemy, raining down fire and darkness. And as this vast, globally encompassing cloud of superheated atmospheric debris, this choking, sunlight-blocking global shroud of fine impact ejecta, then begins to slowly, gradually, and inexorably fall back down towards the Earth's surface from the upper atmosphere, under the relentless pull of planetary gravity, often many long days or even several weeks after the initial primary impact event itself has already long since concluded. It would then effectively and quite catastrophically superheat the entire planet's atmosphere, primarily through the immense frictional drag it would experience as it re-enters the denser, lower atmospheric layers at very high speeds. This re-entry heating would, according to some detailed scientific models, effectively and quite terrifyingly turn the entire sky all across the whole globe into a glowing, broiling, inescapable, and planet-wide convection oven, literally baking the underlying surface of the Earth below with intense, downward radiating infrared heat for many hours, or perhaps even for several days, potentially killing off any remaining surface life that had somehow managed to survive the initial blast. The fires and the winds, then, inevitably, if the impactor was large enough, would come the colossal, almost unimaginable, globe-spanning, and continent-drowning tsunamis. If the impacting asteroid, as is statistically quite likely, given that well over 2/3 of the Earth's entire surface is currently covered by deep water, were to catastrophically strike one of the planet's vast, interconnected oceans, the almost unimaginable, Explosive energy of that underwater impact would then violently displace and powerfully push truly massive, almost unbelievable, towering walls of ocean water outwards at incredible speed in all directions, away from the sub-oceanic impact point. These uniquely impact-generated, colossal ocean waves are predicted to be utterly, qualitatively unlike any ordinary, familiar, and relatively much smaller tsunamis that are typically, and much more frequently, caused on Earth by more conventional geological phenomena. They would be much, much taller in their wave height, potentially reaching many hundreds of meters, or in some extreme impact scenarios, perhaps even several kilometers. In their initial amplitude as they propagate across the deep ocean basins, they would also be much, much faster in their propagation speed, perhaps traveling across entire, vast ocean basins at speeds easily comparable to that of a modern jet airliner, many hundreds of kilometers per hour. And consequently, they would be vastly, unimaginably more destructive, more erosive, and more inundating when they finally, and with little or no warning, eventually reach distant, unsuspecting continental coastlines. Coastal regions, even those that might be located on the very far opposite side of the entire planet from the original remote oceanic impact site, could still be utterly, catastrophically, and completely slammed, many long hours, or perhaps even a full day or more. Later, by these monstrous, towering walls of onrushing ocean water with surging, turbulent waves far, far higher than any currently existing coastal buildings or natural geographical features. Waves that could potentially sweep inland for many, many kilometers, or even hundreds of kilometers in low-lying areas, completely destroying everything, both natural and man-made, that lay within their devastating, irresistible path. The very oceans, cradles of life, would become agents of immense, sweeping devastation. And even after the initial horrific blast wave from the impact has finally, mercifully dissipated its primary energy, even after the searing, incandescent heat has begun to radiate away into space, even after the widespread, raging global fires have at last, perhaps after many weeks or months, finally burned themselves out, and even after the colossal, globe-spanning tsunamis have eventually, after causing unimaginable coastal devastation, finally, gradually receded back into their now churned and debris-filled ocean basins, the truly long-term, insidious, and potentially even more devastating global environmental consequences of such a mega-impact event would, unfortunately, only just then be seriously and inexorably beginning to fully unfold and make their presence felt across the entire planet. The truly vast, almost unimaginable quantities of incredibly fine dust particles, the pervasive black soot generated from the extensive global wildfires, the shattered, pulverized rock debris that was violently excavated from the immense impact crater itself, and various other complex chemical aerosols and vaporized terrestrial and impactor materials that were explosively, energetically thrown up high, high into the Earth's upper atmosphere by the sheer, raw violence of the initial impact event, would then likely remain suspended there in the stable, largely weather-free layers of the stratosphere for a very considerable and potentially quite devastatingly long period of time. This global atmospheric shroud would effectively and quite efficiently block a very significant fraction, perhaps even most, of the incoming, life-sustaining sunlight from ever successfully reaching the planet's underlying surface, potentially for many long, dark, and frigid months, or even, in the case of a particularly large impactor or a very fine-grained ejecta blanket, for several long, difficult, and ecologically catastrophic years. With drastically reduced sunlight levels reaching the surface, photosynthesis, the fundamental biological process that lies at the very base of most, if not all, of Earth's complex ecosystems. The process by which plants and algae convert sunlight into chemical energy would largely, if not entirely, cease on a global scale. Plants all across the world, starved of essential sunlight for their growth and survival, would inevitably and relatively quickly begin to wither, to die, and to decay on a truly massive, planet-wide scale. As a direct and unavoidable consequence of this collapse of primary productivity at the base of the food web, global average surface temperatures would then be expected to plummet dramatically, perhaps by many degrees Celsius, or even by tens of degrees Celsius in some climate models, depending on the amount and duration of sunlight blockage. A kind of artificial, impact-induced, and globally pervasive winter, an impact winter, would then swiftly, inexorably, and quite chillingly settle in across the entire darkened globe. This would be a prolonged period of intense cold and deep darkness. A winter caused not by familiar seasonal variations, but by the profound absence of sunlight at the planet's surface, a chilling twilight for any surviving life. This predicted catastrophic impact winter would in turn inevitably lead to the widespread and likely quite rapid starvation, decline, and ultimate collapse of entire ecosystems all across the world, both on land and in the surface layers of the oceans. Without sufficient sunlight, plants, the primary producers, cannot survive. Without plants, herbivores die. Without herbivores, carnivores perish. Whole, complex food webs that had evolved over millions of years would unravel in a brutal, ecologically devastating period of planet-wide upheaval. The very fabric of life on Earth would be torn asunder. There is at least one chilling, well-documented moment in Earth's history when precisely such a devastating scenario occurred. Approximately 66 million years ago, the Cretaceous-Paleogene boundary event, a colossal 10-kilometer asteroid slammed into what is now the Yucatan Peninsula, creating the Chicxulub crater, over 180 kilometers in diameter. This dinosaur killer is credited with wiping out roughly 75% of all then-existing species. It was not just the impact itself, but the subsequent global wildfires, atmospheric superheating, colossal tsunamis, and, most devastatingly, the prolonged impact winter that followed. Within just a few years, perhaps months, life on Earth was unrecognizably altered. Only the particularly adaptable, often small, organisms managed to survive that global apocalypse. The reign of the dinosaurs ended abruptly, a stark reminder of cosmic indifference. The darkened skies eventually cleared, perhaps after years, and the Earth gradually warmed, but the ecological damage was irreversible. The Chicxulub impact, though uniquely transformative, was not the only such event. Earth's history is pockmarked with scars from other cosmic collisions, some causing regional devastation, others smaller but still locally terrifying. These ancient impacts, evidenced by craters and geological anomalies, remind us that these are ongoing, if rare, processes. Scientists today can simulate these impacts with increasing accuracy, and the predictions are grim. Even a 5-kilometer asteroid could cause civilization-collapsing devastation, obliterating cities, causing global agricultural failure, and leading to widespread societal chaos. Our modern, interconnected world is profoundly vulnerable. The challenge lies in detection. Small asteroids can approach with little warning, while dedicated sky survey programs track larger objects, many smaller, yet still dangerous. Ones pass by undetected until it's too late, or even after they've already passed. Space is vast, and these dark, inert bodies are faint, difficult to spot against the blackness until they are perilously close. International efforts are underway to develop planetary defense strategies, from kinetic impactors like NASA's DART mission to more speculative ideas like solar sails or, as a last resort, nuclear explosives. But these are largely theoretical or in early experimental stages. We have never had to use them in a real emergency. A 10-kilometer asteroid doesn't need to explode. It just needs to land. Its kinetic energy alone is apocalyptic. Despite the danger, there's a grim majesty to these cosmic hammers. They are integral to planetary formation and evolution, delivering water and organic molecules, mixing planetary crusts, and creating new habitats. They are ancient messengers from the solar system's birth, indifferent to our existence, following only the laws of gravity, a constant, if low probability, threat whose melancholy beauty lies in its sheer, transformative, and indifferent power, a power that shaped our world and could, one day, reshape it again. Now, let us broaden our cosmic perspective even further, venturing far beyond the relatively familiar, if sometimes hazardous, confines of our own solar system, out into the vast, dark, largely unexplored, and almost unimaginably empty interstellar realms that lie between the distant, lonely stars. In these quiet, almost unimaginably empty, and incredibly cold reaches of space that exist between the myriad stars of our Milky Way galaxy, there are astronomers now increasingly, and with growing observational confidence, believe countless individual planets that have no home sun, no gravitationally anchoring parent star to faithfully call their own. These are the enigmatic, almost ghostly, rogue planets, the true interstellar orphans of the cosmos, celestial bodies, often of significant planetary size and mass, that were likely, in most cases, unceremoniously, and often quite violently, ejected from their original home planetary systems, perhaps during the chaotic, gravitationally turbulent early stages of their formation around their young, still-forming parent stars. Or alternatively, perhaps they were set adrift, cast out into the interstellar wilderness much later in their system's history, as a direct result of close, destabilizing gravitational encounters with other, more massive planets within their system, or perhaps even with other passing stars or giant molecular clouds that happen to wander too close to their original stellar neighborhood. They now, as a result of these ancient dynamical upheavals, drift, alone, silently, perpetually, and for the most part, almost entirely invisibly to our current telescopes, through the immense, cold, profound darkness of interstellar space, entirely without the life-giving warmth, the illuminating light, or the guiding, stabilizing gravitational embrace of a central parent star to faithfully and predictably orbit. These are often giant, truly wandering worlds, perhaps many of them gas giants as large as, or even significantly larger than, our own Jupiter, or perhaps, and even more intriguingly, from an astrobiological perspective, there are also countless smaller, potentially Earth-sized or Mars-sized rocky bodies among them as well, all forever set loose, untethered from their original home planetary systems, now embarked on an eternal, solitary, and almost unimaginably long journey through the vast, dark, and largely empty expanses of our Milky Way galaxy. Their existence speaks of a dynamic, often violent, youth for planetary systems, a universe less ordered than it might appear. And as these numerous, dark, cold, and incredibly lonely rogue planets move silently, almost ghost-like, and largely undetected, through the immense, almost incomprehensible vastness of our surrounding galaxy, they will, inevitably, from time to time, purely by statistical chance and due to their random motions, pass relatively near to other established and gravitationally stable stellar systems, systems that may well, and indeed often do, contain their own well-ordered families of already existing, gravitationally bound orbiting planets. The statistical chances of a direct, physical, head-on collision between one of these wandering rogue planets and an established planet within such a system are, admittedly, from a purely probabilistic perspective, incredibly, vanishingly small, given the almost unimaginably, truly mind-bogglingly empty nature of interstellar, and even most interplanetary space. But, and this is the crucial and somewhat unsettling point, these chances are not, from a fundamental physical perspective, absolutely, mathematically zero. And if by some incredibly unfortunate, statistically highly improbable, yet physically entirely possible cosmic coincidence, one of these massive, dark, and silently wandering rogue worlds were to actually physically collide, head-on, or even with a significant glancing blow, with another unsuspecting host planet within an established system, especially if that collision were to occur with a planet roughly the size of our own Earth, or perhaps even significantly larger. Like a super-Earth or a mini-Neptune, then the resulting cataclysmic physical consequences, the sheer amount of energy released, would be utterly, almost unimaginably, beyond anything that we have ever directly witnessed or could even readily, intuitively conceive of from our relatively limited and thankfully much more placid terrestrial experience of physical impacts and explosions. A direct, head-on, planet-on-planet collision between two full-sized, massive celestial bodies is not, it must be emphatically stressed, in any way remotely comparable to a relatively small, albeit still potentially devastating, asteroid or comet simply hitting the much larger solid surface of another, much more massive rocky planet. These are entire, fully fledged worlds coming together with unimaginable force, potentially possessing molten cores, thick atmospheres, and perhaps even life. Such a collision is a planetary-scale demolition derby, capable of reshaping or even destroying entire star systems. A true cosmic apocalypse where new worlds are forged in fire from the annihilation of old ones. Imagine a large, dark rogue planet, perhaps Earth-sized or larger, drifting alone through interstellar space for billions of years, its surface frozen under a starless sky, its internal heat slowly fading. By chance, it enters a new stellar system over millennia. Its orbit, influenced by the system's gravity, intersects with an established planet. As they inexorably approach, their mutual gravity accelerates them to a final, spectacular, and mutually annihilating rendezvous. At the moment of impact, the energy released is trillions of times greater than any thermonuclear bomb. The surfaces of both planets melt and vaporize. Mountain ranges are obliterated, oceans flash boil into superheated steam, atmospheres are stripped away and blasted into space. The dense cores of the planets might collide and fuse, forming a new, larger, molten core. The surrounding space fills with a rapidly expanding cloud of glowing debris, shining brighter than nearby stars, a temporary beacon of apocalyptic destruction visible across interstellar distances. If such a collision were to involve an inhabited world like Earth, there would be no warning, no escape. Everything, civilization, ecosystems, life itself, would be utterly erased, buried beneath kilometers of molten rock. Life would not just end, it would be obliterated, its every trace lost in the incandescent chaos. Yet, even in this ultimate destruction, there is a strange, creative potential. The shattered remains of the two planets might, over millions of years, recoalesce to form a single, new, and initially molten world, perhaps larger and more chemically diverse than its progenitors. This newborn world, forged in violence, might eventually cool, develop new geological features, and perhaps, after eons of cosmic convalescence, even become ready for life to arise anew. The universe demonstrates a terrifyingly violent capacity for both destruction and creative renewal. Such world-shattering collisions, though rare in mature systems today, have likely occurred in our own solar system's past. The origin of Earth's moon is widely believed to be the result of a giant impact when a Mars-sized protoplanet named Theia collided with the young Earth. This cataclysm tore off a significant portion of Earth's mantle, which then coalesced to form the moon, forever changing Earth's rotation, axial tilt, and possibly its early evolution. Uranus's extreme axial tilt and Mercury's unusually large core relative to its size may also be scars from ancient giant impacts. These events are not just theoretical. They are part of how planetary systems form and evolve. Scientists estimate there could be as many free-floating rogue planets in our galaxy as there are stars, hundreds of billions, perhaps trillions, drifting silently. They don't even need to collide to cause havoc. A close gravitational pass can destabilize planetary orbits, trigger cometary bombardments, or strip moons from their planets. But a direct hit is a planetary reset button, an event of profound, transformative power. The melancholy beauty here is in the scale of creation and destruction, a cosmic ballet where worlds are unmade and remade. Now, let us turn our gaze from the cataclysmic collisions of entire worlds to the equally, if not more, violent and energetic deaths of individual stars, specifically to a rather peculiar, somewhat rarer, and until relatively recently, not very well understood, type of stellar explosion known as an electron capture supernova. Most people associate supernovae with the core collapse of very massive stars, those more than 10 or 20 times the Sun's mass, ending in a spectacular iron core collapse explosion. But there's another, distinctly different kind of stellar supernova, generally quieter, less luminous, and rarer, originating from stars poised precariously in an intermediate mass range, not small enough to fade peacefully as white dwarfs like our Sun, but not massive enough for the typical iron core collapse. These stars, typically between 8 and 10 or 11 solar masses, die via electron capture. As they near the end of their lives, their cores, rich in oxygen, neon, and magnesium rather than iron, reach a critical density and temperature. Under immense pressure, free electrons are forcibly squeezed into atomic nuclei, combining with protons to form neutrons and releasing neutrinos. This process is known as electron capture or inverse beta decay. Electrons, being fermions, normally provide crucial support against gravity through electron degeneracy pressure, a quantum mechanical effect preventing them from occupying the same quantum state. When enough electrons vanish through capture, this vital pressure support catastrophically drops. With the loss of electron degeneracy pressure, gravity overwhelmingly takes over. The stellar core implodes with shocking rapidity, a near freefall. As material compresses, temperatures and densities soar. Neutrons, newly formed, pack tightly, forming an incredibly dense proto-neutron star at the center. The star's outer layers, rushing inwards, violently slam into this unyielding neutron core. The resulting shockwave rebounds, blasting the star's remaining envelope into interstellar space. This is an electron capture supernova. While not as intrinsically bright as iron core collapse supernovae, these events are crucial. They provide unique clues about stellar evolution, neutron star formation, and the chemical enrichment of the early universe, particularly concerning the production of certain neutron-rich isotopes. They represent a critical evolutionary pathway between the peaceful deaths of low-mass stars and the violent explosions of high-mass stars. Their light curves are often slower, their spectra showing distinct chemical signatures of elements like oxygen, neon, and magnesium, not typically seen in other supernovae. These events may be responsible for a specific subpopulation of neutron stars with characteristic masses, spins, or magnetic fields, and could explain anomalous chemical abundances in ancient, metal-poor stars. They might even trigger new star formation by sending compressive shock waves through nearby gas clouds. The conditions for an electron capture supernova are very specific. The progenitor star must be in a narrow mass range, and its core must develop the right mix of elements at critical densities and temperatures. If the star is too massive, it undergoes iron core collapse. If too small, it becomes a white dwarf. Only a precise evolutionary path leads to this quieter, yet profoundly transformative stellar end. The neutron stars left behind might also be unique, perhaps quieter and less active than those from more violent explosions, slowly cooling as silent reminders of a less spectacular but equally significant stellar departure. Their quiet beauty lies in their subtle precision, a delicate balance tipped into oblivion. Now, let us turn our attention to an even more extreme, even more violent, and certainly far rarer form of stellar death. A cataclysm reserved only for the true celestial titans, the most massive stars that the universe can possibly create, the pair instability supernova. Some stars, it turns out, are born so incredibly, almost unbelievably massive, so astonishingly bright and luminous, and so unimaginably hot in their cores, that the usual well-understood rules and physical processes that govern ordinary stellar evolution and eventual stellar death simply don't apply to them in the same way. These truly colossal stars, behemoths perhaps dozens or even hundreds of times more massive than our own relatively modest sun, relentlessly push the very absolute limits of what fundamental physics itself can seemingly handle, what it can stably sustain. Their entire stellar lives, though incredibly brilliant and impactful on their surroundings, are as a direct consequence of their enormous mass and correspondingly prodigious energy output. Tragically, almost poetically, short, often lasting only a very few brief million years at most, a mere fleeting instant on the vast cosmic timescale. But their spectacular, almost incomprehensible ends, when they finally arrive, are correspondingly some of the most extraordinarily violent, most energetically powerful, and most cosmically significant explosive events that can occur anywhere in the entire universe. And for a very select, very specific few of these ultra-massive stars, those falling within a particular critical mass range, death doesn't come in the usual way, not from the gradual, inexorable collapse of an inert iron core, nor even, as we've just discussed, from a runaway electron capture process in an oxygen neon magnesium core. It doesn't even primarily come from simply running out of available nuclear fuel to burn in their cores. Instead, these unfortunate, uniquely massive stars literally, and quite spectacularly, explode, not primarily because their cores become gravitationally weak and unable to support their own weight, but rather, paradoxically, because their cores become too energetically strong, too incredibly hot and radiation-dominated. They effectively, and quite literally, destroy themselves completely, from the very inside out, in a truly unique and utterly devastating type of stellar cataclysm known to astrophysicists as a pair instability supernova. The universe, in these moments, reveals its capacity for absolute, beautiful annihilation. To even begin to understand how this extraordinary and thankfully very rare type of stellar explosion can actually happen, we have to conceptually look deep into the unimaginably extreme physical conditions that prevail at the very heart, the intensely hot and dense core of such an ultra-massive star as it approaches the very end of its short, brilliant life. In the star's central core region, where ambient temperatures routinely reach many hundreds of millions, or even billions, of degrees Kelvin, and where pressures and densities are almost beyond human comprehension, the star has, throughout its life, been systematically, layer by layer, fusing ever lighter chemical elements into ever heavier ones. Hydrogen becomes helium, helium becomes carbon, and so on, up the periodic table towards heavier elements. This continuous nuclear energy generation creates a powerful outward radiation pressure that normally balances gravity. But in stars exceeding roughly 130 solar masses, as core temperatures surpass several billion degrees, the incredibly energetic gamma-ray photons, which provide this crucial pressure, begin to behave strangely. Instead of just scattering, some transform via pair production into electron-positron pairs. These massive particles contribute little to outward pressure compared to the photons they replaced, as more photons convert to particle-antiparticle pairs. The core's radiation pressure dramatically, catastrophically drops. Gravity, ever waiting, then overwhelmingly takes over, the core, no longer supported, begins a rapid, unstoppable collapse. This is not a gentle fading, but a furious self-destruction driven by the star's own light. As the core contracts, pressures and temperatures build even more rapidly. Then, in a fraction of a second, the entire remaining fuel-rich core, primarily oxygen, neon, silicon, and magnesium, ignites almost simultaneously in a runaway thermonuclear conflagration. Unlike a normal core collapse supernova, this pair instability event explodes without significant prior core collapse to a neutron star or black hole. The sudden, complete fusion of the core floods it with an unimaginable amount of energy. Core temperatures spike to tens of billions of degrees. The entire star is literally, utterly torn apart from the inside out. No dense neutron star remnant is left. No black hole forms. Absolutely nothing of the original star remains, except a vast, rapidly expanding, incredibly hot cloud of newly synthesized gas and plasma, rushing outwards at thousands of kilometers per second. The star is not just disrupted, it is completely, irrevocably annihilated. This explosion comes not from running out of fuel, but paradoxically, from the star's own intense light becoming its agent of destruction. A runaway positive feedback loop culminating in total stellar self-destruction. The melancholy beauty of this event is its completeness. A star erased utterly from existence, its matter flung wide to enrich the cosmos. These titanic pair instability supernovae are exceptionally rare today, predicted only for stars born within a narrow mass range, roughly between 130 and 250 solar masses. Smaller stars might experience some pair instability but survive partially, perhaps shedding mass in violent pulsations before a more conventional collapse. Even larger stars might collapse directly into a black hole without such an explosive event. Unlike other supernova, pair instability supernovae, by completely disrupting the star, release truly huge quantities of elements like oxygen, carbon, and silicon into interstellar space. These elements then become crucial building blocks for future generations of stars, planets, and potentially life. Astronomers suspect these explosions were more common in the early universe, when the first generation of stars, population 3 stars, are thought to have been much more massive and metal-poor. These colossal first stars likely ended their lives as pair instability supernovae. Seeding the young cosmos with its first heavy elements, the James Webb Space Telescope is actively searching for the faint, ancient light from such primordial explosions. A few tentative candidates for more recent pair instability supernovae have been observed, such as SN 2007bi, an unusually bright and long-lasting supernova whose properties match theoretical models almost perfectly. These events are crucial for understanding cosmic chemical evolution, explaining how certain elements appeared in large abundances so early in cosmic time. Each such explosion is a violent act of cosmic alchemy, transforming primordial simplicity into elemental complexity. Now, let us explore the dramatic ballet of stellar mergers, where binary stars, their orbits decaying over eons, spiral into a final, fiery coalescence. Many, perhaps most, stars exist not in isolation, but in gravitationally bound pairs, over vast timescales. These binary stars can lose orbital energy through gravitational wave emission or tidal interactions, causing them to spiral inwards. If this inward spiral continues, a catastrophic physical collision is inevitable. Stars are not solid objects but spheres of hot plasma. When they finally touch, their outer gaseous layers intermingle and violently interact. Their dense cores are drawn closer, distorting each other until they merge into a single, larger, hotter, and often rapidly rotating, unstable object. The outcome depends on the masses, evolutionary stages, and compositions of the merging stars. If two main sequence stars of similar mass merge, they can form a new, more massive main sequence star, appearing brighter, hotter, and living a shorter life. Such objects might explain blue stragglers in old globular clusters, stars that appear anomalously young. Their youthful glow hides the violent merger that created them, a creative act born from destruction. However, not all stellar mergers are so neat. If one or both stars are more evolved, like a red giant, or if their masses are very unequal, the merger becomes incredibly messy and dynamically complex. A larger, diffuse star might engulf its smaller companion, leading to a common envelope phase where two cores orbit within a shared, turbulent gaseous envelope. Friction can heat this system intensely, often ejecting the common envelope, leaving behind a very close binary of the surviving cores. Or if the cores also merge, a single, highly evolved, rapidly rotating remnant. Sometimes, the energy released during such a merger creates a luminous red nova, a bright, reddish optical outburst less powerful than a supernova, but still visible across vast distances. One famous example was observed in 2008 in the Andromeda Galaxy. Another V1309 Scorpii in our galaxy was observed just as two contact binary stars merged, providing an unprecedented view of the entire process from inward spiral to final coalescence. Its brilliant glow was the direct thermal radiation from the moment of stellar contact, a testament to the universe's capacity for sudden, blazing transformations. When very massive stars merge, the outcomes are even more dramatic and energetically powerful. Vast quantities of stellar material are compressed, heated, and violently ejected. Their combined cores might ignite new, rapid phases of thermonuclear fusion. The turbulent mixing of elements can create spectacular light flashes and unusual chemical signatures. These newly formed, incredibly massive merged stars burn through their fuel at prodigious rates, dying young in spectacular supernova explosions far sooner than their progenitors would have. In some rare cases, the merger of massive stars or compact remnants like neutron stars or white dwarfs might even produce gamma-ray bursts, some of the most luminous explosions in the universe. Long gamma-ray bursts, in particular, might arise from the collapse of massive merged stars rotating so rapidly that they launch narrow beams of high-energy radiation. Even our own Milky Way galaxy is destined for a galactic-scale merger with Andromeda in billions of years, While individual stars are unlikely to collide directly due to vast interstellar distances, their orbits will be profoundly disrupted, potentially triggering stellar mergers within destabilized binary systems. The universe is a place of constant dynamic interaction where even the stately dance of stars can end in a violent, transformative embrace, scattering the seeds of future creation across the void. Each merger is a unique cosmic event, its fingerprint etched onto the surrounding environment, a story of union and upheaval written in light and gravity. Our journey now plunges into realms of unimaginable density, into the very heart of matter crushed beyond recognition. Beginning with neutron stars, these are the incredibly compact cores often left behind when a large star, typically between 8 and 25 times the Sun's mass, exhausts its fuel and dies in a supernova. A neutron star is astonishingly small, perhaps only 20 kilometers across the size of a large city, yet it packs more mass than our entire Sun. This extreme compression results in surface gravitational fields billions, even trillions, of times stronger than Earth's. Anything venturing onto its surface would be instantaneously and catastrophically crushed, its atoms torn apart by irresistible tidal forces and unimaginable pressure. The key to this is the extraordinary density of neutron star material. On Earth, we understand density in terms of how heavy something is for its size. But neutron star densities transcend terrestrial experience. Ordinary atoms cannot maintain their structure. Under the immense pressure, electrons are forced into protons, forming neutrons. These neutrons are packed shoulder to shoulder with almost no space between them, like a giant, city-sized atomic nucleus. A single teaspoonful of this matter would weigh around 10 million tons, more than all the buildings in a major city. The sheer weight of such density bends space-time itself, a silent testament to gravity's ultimate power. The outermost crust of a neutron star is thought to be a thin, incredibly rigid layer of atomic nuclei and degenerate electrons, with atoms stretched into long, needle-like chains by the intense gravity and magnetic fields. Deeper inside, conditions become even more exotic and less understood. Nuclei dissolve, and neutrons may behave as a quantum superfluid, flowing almost without friction. Deep within the core, pressure warps space-time significantly. Time ticks more slowly near a neutron star's surface compared to a distant observer, a phenomenon of gravitational time dilation. Light paths are visibly bent, allowing an observer to potentially see more than half the star's surface at once. Born from the collapse of rapidly spinning stellar cores, neutron stars typically rotate very quickly due to conservation of angular momentum. Many spin several times a second. Millisecond pulsars, often spun up by accreting matter from a binary companion, can complete hundreds or nearly 1,000 rotations per second. These rapidly spinning, highly magnetized neutron stars are observed as pulsars, emitting beams of radiation from their magnetic poles. Each sweep of a beam across our line of sight registers as a precise pulse. So regular, they rival atomic clocks and are used in projects to detect long-wavelength gravitational waves. The gravity's effect on infalling matter is profound. A pebble hitting a neutron star's surface would do so at about half the speed of light, releasing an enormous burst of energy. This is why X-ray binaries, where a neutron star accretes matter from a companion, are so intensely bright in X-rays, as infalling material crashes onto the neutron star, heating its surface to millions of degrees. The exact state of matter at the very center of a neutron star, where pressures are even more extreme, remains a subject of intense theoretical debate. Some models suggest neutrons might deconfine into their constituent quarks, forming quark matter or a quark gluon plasma. Others propose the existence of exotic hadronic particles like hyperons. These conditions are impossible to replicate on Earth, making direct experimental verification elusive. What prevents a neutron star from collapsing further into a black hole is neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which forbids identical fermions like neutrons from occupying the same quantum state. This pressure supports the star against gravity up to a critical mass limit, the Tolman-Oppenheimer-Volkoff limit, estimated to be around 2 to 3 solar masses. If a neutron star accretes too much mass and exceeds this limit, even neutron degeneracy pressure fails, and it collapses catastrophically into a stellar mass black hole. Neutron stars also possess incredibly strong magnetic fields, sometimes trillions or quadrillions of times stronger than Earth's. These ultramagnetic neutron stars, known as magnators, can experience violent starquakes in their crusts, releasing huge flares of gamma rays and X-rays. A powerful magnetar flare from a nearby source could potentially damage Earth's atmosphere and biosphere. Though thankfully, all known magnetars are safely distant. These crushed cores, spinning with furious speed and wrapped in unimaginable magnetic fields, are laboratories for extreme physics, their existence pushing the boundaries of our understanding of matter and gravity. Now, let us consider an even more speculative, yet theoretically plausible, and potentially even more energetic cosmic event, the quark-nova conjecture, which proposes the possibility of a hypothetical, powerful second blast occurring shortly after a star has already died in a supernova. For decades, it was thought that matter couldn't be packed more tightly than in a neutron star, unless it collapsed into a black hole. The quark-nova idea challenges this "what if?" Under even more extreme conditions, the story doesn't end with stable neutron matter. If the internal pressure within an existing neutron star continues to rise, perhaps due to rapid accretion or a subtle shift in core conditions, it might cross a new critical stability limit. At this point, the quark-nova theory suggests individual neutrons could deconfine, dissolving into their constituent quarks, forming an even denser state of matter known as quark matter, or a quark-gluon plasma. This phase transition from neutron matter to quark matter would likely cause a sudden, violent, additional gravitational collapse of the neutron star's core, followed by an equally violent, explosive bounce back. The energetic result would be a powerful, distinct second stellar explosion, a quark nova. This secondary blast, following the primary supernova by perhaps hours or days, would send out another burst of energy, particles, and possibly newly synthesized elements, significantly reshaping the supernova remnant. If quark novae are real and occur with significant frequency, they could explain anomalous features in some supernova light curves and spectra, such as unexpected rebrightenings or unusual emission lines that standard models struggle to account for. These secondary explosions might offer a window into physics beyond the neutron star state, a realm of even more extreme matter. Some theoretical models of quark novae suggest this secondary explosion could launch its own relativistic jets or release distinct bursts of gamma rays, potentially contributing to the brightest superluminous supernovae. Furthermore, while normal supernovae forge many heavy elements, the incredibly neutron-rich environment of a newly formed neutron star is ideal for the R process, creating elements far beyond iron. If a subsequent quark nova disrupts this neutron-rich core, it could scatter these very heavy, rare elements into space, their unique chemical fingerprints potentially appearing in ancient beige, metal-poor stars or future planetary systems. An even more speculative outcome is the formation of stable, strange quark matter. Some theories propose that once deconfined quark matter forms, it could be even more stable than ordinary nuclear matter. If a seed of this ultra-stable strange quark matter appears, it might trigger a runaway conversion of the entire neutron star into a quark star, an even more exotic and compact remnant. These purely hypothetical quark stars remain unobserved, but represent a possible end state for matter under extreme pressure. A quark nova could be the transformative process creating them, tiny fragments of this strange quark matter. Strangelets might even be ejected, flying invisibly through the galaxy. Verifying these theories is challenging, as we cannot replicate such extreme conditions on Earth. However, the quark nova idea offers an intriguing lens to understand the complex final moments of some massive stars, suggesting that even after a star has died once, something deeper, more fundamental, can break free, unleashing enough power to rip its core apart one final spectacular time. The universe, it seems, may hold layers of explosive potential within its densest objects, a series of apocalypses nested within each other. The journey into extreme cosmic events now brings us to kilonova explosions, born from the cataclysmic mergers of neutron stars, serving as cosmic forges for the rarest elements in the quiet corners of the universe. Two neutron stars, remnants of massive stars, can orbit each other in a slow death dance lasting millions or billions of years. Due to the emission of gravitational waves, ripples in spacetime predicted by Einstein, their orbital energy slowly drains, causing them to spiral inexorably closer. Their orbital speeds increase dramatically, approaching a significant fraction of the speed of light in their final moments. Eventually, they catastrophically collide, unleashing one of the most powerful and scientifically informative explosions, a kilonova. These events are rare, perhaps occurring only once every few tens or hundreds of thousands of years in a galaxy like the Milky Way. As the neutron stars merge, the system emits increasingly strong gravitational waves. When they finally crash, they tear each other apart. Huge amounts of incredibly dense, neutron-rich matter, perhaps many moon masses or even a few percent of a solar mass, are violently flung into space at extreme speeds, often approaching 1/3 to 1/2 the speed of light. This ejecta is uniquely neutron-rich, creating perfect conditions for the R process. In the rapidly expanding, cooling ejecta, free neutrons are rapidly captured by lighter atomic nuclei, building up progressively heavier, unstable isotopes. These then undergo radioactive beta decays, transmuting into more stable, heavier elements. In mere seconds, complex chains of very heavy elements, like gold, platinum, silver, and uranium, are formed. These elements are not significantly produced in ordinary stars or most supernovae. Kilonovae are believed to be their primary cosmic source. Without these rare events, such precious elements would be virtually non-existent. The light from a kilonova is distinctive. Its brightness rises very quickly, within a day or two of the merger, reaching a peak luminosity often comparable to or slightly less than a typical supernova. It then fades rapidly over a week or two. Its color evolves dramatically, typically from an initial hot, bright blue to a cooler, fainter, redder, or near-infrared hue as heavy R-process elements form and increase the ejecta's opacity. In 2017, astronomers witnessed GW 170817, the first confirmed kilonova, detected through both gravitational waves and subsequent electromagnetic radiation across the spectrum. Two neutron stars merged about 130 million light-years away. The gravitational waves arrived first, followed seconds later by a gamma-ray burst, and then by optical and radio afterglow. This event is estimated to have produced dozens of Earth masses worth of heavy R-process elements, including enough gold to fill Earth's oceans many times over. A few such events over billions of years can significantly enrich vast regions of interstellar space. What remains after the merger depends on the total mass. If it exceeds the Tolman-Oppenheimer-Volkoff limit, the remnant likely collapses rapidly into a black hole. If slightly less, a hypermassive, rapidly spinning neutron star might form temporarily before collapsing. During this brief phase, strong, wound-up magnetic fields and rapid rotation can launch powerful relativistic jets, believed to produce short-duration gamma-ray bursts, lasting less than 2 seconds. Gravitational wave detectors like LIGO and Virgo allow scientists to pinpoint these mergers and alert other telescopes, enabling multi-messenger astronomy. By studying the light and spectra of kilonovae, we learn how heavy elements form, how the explosion evolves, and what kind of remnant is left. Much of the gold, platinum, and uranium in our solar system likely originated from ancient kilonovae, their elemental bounty incorporated into the clouds that formed our Sun and Earth. We literally carry the results of these distant, violent stellar collisions, a tangible link to the universe's most creative and destructive moments, a melancholy beauty in the ashes of dead stars reborn as precious matter. Our exploration now confronts the universe's most extreme engines, beginning with magnetars, neutron stars wielding magnetic fields of such incomprehensible strength they can trigger starquakes and colossal gamma-ray flares. These are true magnetic leviathans. A typical magnetar's magnetic field can be 1,000 times stronger than a normal neutron star's, reaching up to a quadrillion times stronger than Earth's geomagnetic field. These fields are so potent they don't just influence nearby space, they actively reshape matter itself, distorting atoms, altering chemical bonds, and even affecting the quantum vacuum. Light behaves strangely near such fields, becoming polarized or scattered in unusual ways. Even empty space near a magnetar's surface can act like a prism, bending light. Most of the time, magnetars are relatively quiet, rotating slowly and emitting low levels of X-rays or gamma rays. But then, without warning, they can erupt in giant flares. In less than a second, a magnetar might release more energy than our Sun does in 100,000 years. These flares are not from nuclear fusion or gravitational collapse, but from the magnetic field itself. Over time, the field twists and strains the magnetar's solid crust. Like Earth's crust cracking in an earthquake, the magnetar's crust can snap. The stored magnetic energy is released all at once as a massive outburst of gamma rays and X-rays. One famous flare on December 27, 2004, from SGR 1806-20. Temporarily altered Earth's ionosphere and overwhelmed satellite detectors. If it had been much closer, it could have caused significant atmospheric damage. These events are rare, but highlight the immense, dormant power locked within these objects. These giant flares are rare, but smaller bursts might happen more regularly, especially in young magnetars. Even these can rival the Sun's energy output. Magnetars exist at the edge of known physics, their fields challenging quantum theory and general relativity. No terrestrial laboratory can replicate these conditions. They are natural crucibles for extreme physics. There's also a potential link between magnetars and fast radio bursts, powerful millisecond duration radio pulses of unknown origin. In 2020, a magnetar in our galaxy emitted a radio burst simultaneously with X-rays, suggesting a connection, though the burst was weaker than FRBs from distant galaxies. Magnetars are thought to have short active lives. Their magnetic fields decay over thousands of years, and they eventually become quiet neutron stars. This makes them hard to find, with only a couple of dozen candidates known. Satellites like Swift and Fermi constantly scan for high-energy flashes, hoping to catch these fleeting eruptions. The exact formation mechanism of magnetars remains debated. Perhaps they are born from very massive, fast-spinning stars, or perhaps from post-supernova interactions. Regardless, once formed, a magnetar is a ticking time bomb. its serene surface belying the magnetic fury within, a beautiful yet terrifying concentration of electromagnetic power. Fast radio bursts, first detected in 2007, remain one of modern astronomy's great mysteries. These are millisecond-long flashes of incredible radio power, appearing suddenly and then vanishing. Unlike predictable signals from pulsars or quasars, FRBs are enigmatic. They release as much energy in a millisecond as the sun does in a day. Yet their sources are often invisible in other wavelengths. Initially suspected as glitches, their consistent detection from deep space confirmed their astrophysical reality. Theories abound. Some suggest they are related to explosive events in massive stars or the collapse of dense objects like magnetars. The connection to magnetar flares is compelling. Others propose cataclysmic events involving black holes, like collisions or a black hole consuming a neutron star, though direct evidence is lacking. More exotic theories, including signals from advanced extraterrestrial technology, are considered, though without concrete support. Most FRBs are single flashes, but some repeat at random intervals, suggesting a non-catastrophic, repeatable source. These repeaters offer better opportunities for study. All detected FRBs originate outside the Milky Way, often billions of light-years away, their immense power challenging our understanding of energy generation. As radio waves from FRBs travel through intergalactic space, they interact with electrons, causing delays and scattering. Studying these effects provides insights into the diffuse matter between galaxies. Repeating signals hint at active magnetars or neutron stars in binary systems, where intense magnetic fields create periodic bursts. Observatories worldwide continue the hunt, seeking to unravel the origin of these powerful, fleeting cosmic whispers, signals that briefly illuminate the vast, dark voids. Their ephemeral nature holds a certain melancholy beauty, like messages in bottles cast into the cosmic ocean. Finally, we confront the ultimate engines of cosmic power black holes and the dramatic phenomena associated with their insatiable hunger. Black hole formation itself is a testament to gravity's relentless might. When a truly massive star exhausts its nuclear fuel, its core collapses under its own weight. If the star is sufficiently massive, even neutron degeneracy pressure cannot halt the collapse. The core implodes, shrinking towards infinite density, forming a singularity. Around this, an event horizon materializes, the point of no return, beyond which nothing, not even light, can escape. While the black hole is hidden, its birth is often announced by a supernova explosion, releasing vast energy as neutrinos, electromagnetic radiation, and shock waves that disperse heavy elements and can trigger new star formation. Many stellar mass black holes exist in binary systems, accreting matter from a companion star. This infalling material forms a hot accretion disk, emitting intense X-rays that allow us to detect and study the black hole's properties. Sometimes, these black holes merge with other compact objects, emitting detectable gravitational waves. The very existence of black holes, with their singularities and event horizons where known physics breaks down, challenges our fundamental understanding of the universe, a profound mystery at the nexus of gravity and quantum mechanics. Black hole hyperaccretion represents an even more extreme phase, where black holes feed at rates far beyond their usual capacity. The accretion disk becomes supercharged, with matter spiraling inward at near-relativistic speeds. This frenzy generates massive, collimated jets of plasma and radiation, blasting outwards for millions of light-years, making these objects some of the most powerful and luminous in the universe. This typically occurs when a large influx of matter from galactic mergers, gas clouds, or tidally disrupted stars becomes available. The accretion disk heats to millions or billions of degrees, emitting vast radiation across the spectrum, often outshining its entire host galaxy by factors of thousands or millions. This powerful radiation can even push away infalling material, creating a self-regulating feedback loop. The jets launched during hyperaccretion are thought to be driven by powerful magnetic fields generated by the spinning black hole and the turbulent accretion disk. Material from the innermost disk is accelerated and funneled outwards along the black hole's rotational axis. These jets are visible across cosmic distances, especially from active galactic nuclei in young, distant galaxies. The energy carried by these jets can profoundly influence the host galaxy, heating interstellar gas and suppressing star formation, a process known as AGN feedback, crucial for regulating galaxy growth. Quasars are iconic examples of hyperaccreting supermassive black holes, initially appearing star-like. Their large redshifts revealed them as incredibly distant and luminous galactic centers, their light often taking billions of years to reach us. They offer a window into the early universe, allowing study of early black hole and galaxy evolution. The intense radiation from quasars also played a key role in cosmic reionization, transforming the early universe from a neutral, opaque fog to the transparent, ionized state we see today. Blazars are an even more extreme class of AGN, where the relativistic jet happens to be pointed almost directly at Earth. This alignment causes relativistic boosting, dramatically amplifying the jet's apparent brightness and energy due to the principles of special relativity. Blazars are among the most energetic, luminous, and rapidly variable objects known. Their jets can outshine the entire accretion disk and host galaxy, their brightness fluctuating on timescales of hours or days due to turbulent processes within the jet. This rapid variability allows us to probe the innermost regions near the black hole and the jet launching mechanism. Blazars emit radiation across the entire electromagnetic spectrum, from radio waves produced by synchrotron radiation to high-energy X-rays and gamma rays from inverse Compton scattering. Their distant light, traveling for billions of years, can be used as a probe of the intervening intergalactic medium and the large-scale structure of the universe, even offering indirect ways to investigate dark matter and dark energy. A famous example is 3C279, a benchmark object for studying relativistic jets. The Fermi Gamma Ray Space Telescope has been instrumental in discovering and studying many blazars at high energies. These cosmic lighthouses, powered by the universe's ultimate engines, illuminate the deepest, darkest, and oldest corners of existence. A more transient, yet equally spectacular display of black hole power is the tidal disruption event, when an ordinary star wanders too close to a galaxy's central supermassive black hole. The black hole's immense tidal forces, the difference in gravitational pull across the star, can overwhelm the star's own gravity. The star is stretched into a cosmic spaghetti strand and violently torn apart. This disintegration releases a brilliant, short-lived burst of radiation, primarily in ultraviolet and soft X-rays, as stellar material is shredded, accelerated, and compressed. Unlike persistent AGN accretion, TDEs are fleeting, one-off events. Much of the disrupted debris is scattered into eccentric orbits, with only a fraction falling back to form a temporary, luminous accretion disk, causing a dramatic spike in the black hole's luminosity. The energy released can briefly outshine the entire host galaxy by hundreds of times, making TDEs visible across vast cosmic distances. Such events occur when a star's orbit is perturbed, perhaps by interactions within the dense central star cluster. Once a star crosses its tidal radius, its demise is inevitable. The ejected stellar material, enriched with elements forged in the star's core, is spread through the host galaxy, influencing its chemical evolution. Observing the TDE flare's light curve, color, and spectra provides unique clues about the black hole's mass and spin. and the physics of extreme accretion. However, these events are short-lived, often fading within months, making them challenging to detect and study in their crucial early stages. Each TDE is a brief, violent illumination of a black hole's destructive power, a star's final scream echoing across the cosmos, a melancholy testament to the indifferent gravitational titans that lurk at the hearts of galaxies. Our voyage through the realms of cosmic power, from the whisper of a lone particle to the roar of colliding galaxies, draws to a close. We have witnessed the universe in its most extreme states, where energy and matter are forged and annihilated in crucibles of unimaginable scale. We have seen stars born from violence and dying in spectacular, element-scattering explosions, worlds adrift and worlds consumed, and the silent, inexorable dominion of gravity, culminating in the enigmatic darkness of black holes. What is the most powerful thing in the universe? Perhaps it is not a single entity, but the relentless, transformative process itself. The constant interplay of creation and destruction, the delicate balance forever teetering on the edge of cosmic apocalypse. The melancholy beauty we find in these events is not in the destruction itself, but in the profound, indifferent grandeur of the cosmos. A universe that operates on scales and with forces so far beyond our terrestrial experience that they inspire both awe and a deep humility. These cosmic titans, from supernovae to quasars, are not merely destructive. They are integral to the universe's ongoing evolution, scattering the very elements that make up stars, planets, and ultimately ourselves. We are, in a very real sense, forged from the ashes of these cosmic fires, our existence a fleeting, intricate dance on a small stage in a vast, dynamic, and often violent cosmic theater. As we continue to peer deeper into the void, armed with ever more sophisticated instruments and an insatiable curiosity, we uncover more of these powerful secrets. Each discovery reminds us of how much we still have to learn, how many more layers of reality await our understanding. The universe does not yield its truths easily, but in every answered question, new, more profound mysteries emerge. The quest to comprehend these ultimate powers is a journey into the heart of what it means to be a conscious observer in such a universe. A tiny spark of awareness capable of contemplating the infinite, and in that contemplation, perhaps, lies a power of its own, the power to wonder, to explore, and to find a strange, poignant beauty in the ephemeral light against an eternal, powerful darkness. The echoes of cosmic fury will continue to resonate, shaping the universe long after our brief moment has passed, a timeless symphony of power and transformation.